to this. Yeah, okay, great. Well, welcome everybody, online and in person here. We're going to be talking about induction for the next 3 hours. There's a few of you in this classroom that I taught induction to, so I'll be asking you repeatedly for answers. No, I'm just kidding. But call-outs are great. I'll definitely want help from the audience. The way I'm going to do this, I'm going to start off by introducing it as if it's new. So again, those of you who learned it from me have seen some of these beginning slides. And after maybe the first 30, 40, 50 minutes of sort of the easy versions, I want to get into some really, really nice induction proofs that I'm quite fond of. Yeah, good. So, well, maybe I can erase this. And then, oh, I could have addressed the joke, but oh well. So let's see here. So switch it there. Oh, is it not?
The audio's good.
The audio is good? Okay, okay. But I see what's happening here. I think this will progress it now. Great. Okay, so I'm going to start with this warm-up problem. This is the canonical warm-up problem to induction, I think. And once I solve this, or discuss this, we'll get into the actual formal induction, and we'll use it to prove this using that framework here, okay? So I want to look at sums of the first n natural numbers, of odd natural numbers, and try and find a pattern, and then see how I can use that pattern to help me like prove a formula for it, right? If you look at the problem here, it's begging for a formula, right? It says, what is the sum of the first n odd natural numbers? It should be a formula in terms of that n itself, okay? So let's try and generate some instances to get an idea. So what is the sum of the first one many odd integers? It's a little bit weird, right? But it's literally the number 1 by itself, the sum of just 1. So the first sum is 1, and that equals 1. Right? That's not enough to get a formula, obviously. So how about the sum of the next, or the first two? Right? 1 plus 3, perfect. Brain buster there, it's 4. Right? Now the sum of the first 3 odd integers is 1 plus 3 plus 5. Let's write those down and see if we get something. 1 plus 3 plus 5. What do we get there? Very nice, 9. And then the next 1 plus 3 plus 5 plus 7. You guys can call it out. I know it's not challenging, but 16, right? What do you think is going to be the sum of the first 5 odds based on the pattern we're starting to see here? Any guesses? I'm sure you see the pattern, right? 32 is a really good guess, actually, but this 9 throws it off here, right? It does seem like powers of 2, but what other pattern are we seeing there? Yeah, those are perfect squares, right? So how about 25? And let's check, right? That's a guess for the moment, but 1 plus 3 plus 5 plus 7 plus 9, right? You can add these up, you get 10, 10, 5 equals 25. Let's do one more. 1 plus 3 plus 5 plus 7 plus 9 plus 11. And now I want to highlight something really important here. We can compute this. It's not hard to just sit down and add all the numbers up here. What's the shortcut, though? There's a shortcut that we can do this computation with. Right? If I'm trying to sum up the odds 1 up to 11, yeah, exactly, right? I already have this sum computed in the previous, right? That's literally 1, 3, 5, 7, 9. I already did that by hand to find it's 25. So I can shortcut this a little bit by saying, oh, well, that's 25, and I'll add to it 11, and this gives me 36, right? And certainly that'd work for the next one, right? If I want to know the next, what am I going to be asking for here? Well, it'll be 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13. But I can just use the 36 that I already know, that computes this list here, and add to 36 what? The next odd, which is 13, and this will give me 49, right? I'll just write this one out again. 7 plus 9 plus 11 plus 13, okay? And so now we're really starting to see a pattern. We have lots of evidence for this pattern in particular. I'll write it out in just a moment here. But one thing I want you to keep in mind for when we learn induction was this sort of shortcutting step. You might wonder if that's maybe a coincidence, and maybe it is a coincidence, but we can still use it to great effect to prove the following formula here. Okay, so let's try and write it out in general. So let's say I'm looking at the first, oh, that's probably just out of view, isn't it? Yeah. Okay. So first n odds, their sum, let's write it out as follows, It's 1 plus 3 plus 5 plus, and now we have to do a little bit of thinking here. I want this formula in terms of n. What is the format of the nth odd number? It's easy to get off by one error here. Yeah?
2k plus 1.
It's 2n. Of course, you meant n, right? That's the variable we're using here. And it's actually, I think it's minus 1 here. Let's just check, though. You have the right idea. 2k plus 1 is definitely an odd, or 2n plus 1 is definitely odd. But think about it this way. This one here was the first odd. So if I plug in n equals 1, I get 2n minus 1 to give me 1. And then 2 times 2 minus 1 to give me 3. 2 times 3 minus 1 to give me 5. And so the nth odd is actually 2n minus 1 there, right? Does that match up there? This is a classic one. That's reasonable too. Are you a computer scientist? Yeah. Perfect. So yeah, and it can be, if you zero index, we just get a different formula. Everything still works though, certainly. Okay, so that's sort of abstractly how to write out the first n odd numbers. And then according to the formula we've seen here, what does that seem to be? The first 1 odds is 1. The first 2 is 4. The first 3 is 9. What seems to go on the, I'm going to put it on the right-hand side, but what appears to go there according to our pattern here?
Even sides.
Oh, okay, that's very wise. Actually, even a square, right? Oh, is that a rectangle with even sides? Okay, yes, exactly. And so, yeah, let's add this actually. This will help us out, right? 1 is 1 squared. 4 is 2 squared. 9 is 3 squared. Forgive the pedanticness for now. You'll be begging me to go back to this later, but so 1 squared, 2 squared, 3 squared, 4 squared, and so on. And so this 7 squared is the number of terms here, right? This 6 is the number of terms here. And so if I'm summing the first n odds, it appears that we should be getting n squared, okay? For the moment, that's a conjecture. That's just based on this pattern here. It's quite a beautiful statement though, right? If you add up these odd numbers in a row, you get a perfect square, which is somewhat remarkable. A warning here that you can't take patterns like this for granted and say that's the truth, right? I think those of us that have had a few math classes have learned this. I went and searched on Stack Exchange a few nights ago out of curiosity about patterns that hold for a while and then fail eventually. There's a classic one with prime numbers that holds for the first n 41 values. It's like true, 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 true for 41, and then at the 41st or 41st it fails. But people have come up with examples that hold for like billions and billions and billions and then like break. You can contrive them as well, but the lesson is like this is not a proof of that. We want to prove that using this somehow. Okay, so let's try and think about this case here, where I think this was the one we looked at especially. Compare these two lines, where I went from the 5 case to the 6 case, and I used this sort of like substitution where I was like, oh, I knew this is 25 because I computed it by hand. Let me plug it in here and see what happens, okay? And let's see if we can figure out how to do this in this abstract setting here. So let's imagine for a second that I want to establish this statement here, and I don't know that it works for the first n odds, but suppose that I know that it holds for the first n minus 1 odds. Okay? Let's just imagine that I knew that somehow, some way. I don't know how. I mean, in fact, it seems like the same statement. But this is the analog of going from the 25 to the 36. I knew this one because I computed it, and this helped me compute this one. Let's see if we can get this to work here. So suppose for the sum of the first n minus 1 odds is the following formula. What do we think that's going to sum to? Yeah, n minus 1 squared, right? It's actually just this formula up here with n minus 1 replacing n. That'd be the same formula with one less variable. And so we get 1 plus 3 plus 5 plus, you can think about this for a second, but this is 2n minus 1 minus 1. But clearly 2n minus 3 is the one prior odd number before the 2n minus 1, right? It's 2 less, okay? So let me put this in red for a second. We don't really have any reason to believe this is true, but just a little suspension of disbelief for now. Let's just imagine this red box thing I told you was true, and I want to use this magic information to establish this here, okay? And then I'll tell you exactly what induction is, but this is basically induction in disguise. Let me erase the evidence here, but again, remember, I want to remind you that we're going from the 25 to 36. This is our idea here. It's just sort of abstract from the n minus 1 to the n. Okay, so I am erasing that case, but let's think about how we did this. When we tried to compute the sum of the first 6 odds, we plugged in the answer for the sum of the first 5 odds and then did a little easy arithmetic. Right? Actually, let me write that down again because I think it really helps. What was this one? This was 7, 9. Is that right? This is 25? We had that, and then I asked 1 plus 3 plus 5 plus 7 plus 9 plus 11. And what we did with this would say, oh, hey, that's 25. Then plus 11 equals 36, right? And of course, it's not hard to just compute that directly, but we had this substitution, right? If you were writing a little program, you can make the substitution here to be a little bit faster. So I want to take the analog of that over to this setting here. So I want to establish this one given this one. So let's write down the left-hand side of this. 1 plus 3 plus 5 plus, and this terminates at 2n minus 1. And because it's going to help me out here, what's the term prior to this in this? It's hidden in the dot, 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 but what's the name of the term prior here? Yeah, 2n minus 3, right? We didn't write it in the dot, dot, dot above. I mean, at some point you have to have a dot, dot, dot if you go from concrete values to an abstract one here, but that is actually sitting around there. Okay, and then I'm hoping to find that this equals n squared, but I don't know how to do that yet. So I'm looking at this sum here. And what does the thing boxed in red tell me about this? What's the substitution I can make? Think about this analog. In fact, let me use purple for that. So here I said, hey, that part there, all but the last term, I can substitute it in using that. So let's do the same thing here. This here, I can make a substitution by the red thing there. The red thing is exactly what's here. Right, 1, 3, 5 up to 2n minus 3. And I told you, right, some oracle said, hey, that's n minus 1 squared. All right, so I'm going to plug that in. N minus 1 squared. And then plus, don't forget, that's still hanging about 2n minus 1. Everybody okay with that? All I did was a substitution presupposing this information here. Okay? And now what would you do with this? Yeah, let's expand, simplify, just try to make it nicer, right? I want to FOIL things out. I don't like them when they're like this. So okay, let me just put equality here, right? This purple went into that. And let's expand. What happens when I expand? N squared minus 2n plus 1 plus 2n minus 1, right? I just wrote everything out. And what fantastic thing happens to this? Yeah, 2n's cancel, the 1's cancel. This turns into n squared. What's the significance of n squared? It's what we wanted, exactly, which is what we wanted. A common, that's a replacement for QED, which is what we wanted. That was this thing here, okay? So the idea was that if I had this information, I could somehow use it as a substitution into this to get the answer I desired, because now look what I've shown. This sum here equals this quantity here. But that's the thing I was hoping to establish, okay? And this is what induction allows you to do. And so on the next slide, I'm going to draw like the abstract definition of the principle of induction that captures all of this. And then I'll justify it too with sort of a hand-wavy argument. I won't be any more formal than that, although it's not hard to prove. And then I will use it, to go through this argument a little more formally, although it'll look almost identical. And then we'll get into the meat of it and start proving problems from scratch, okay? All right. Yeah, go ahead and go to the next one. That's the statement there. And Hannah, you can even show the dominoes underneath it. We can sort of dwell on that at the same time. Okay, so here's the principle of induction or mathematical induction. And it's a bit of a monster, but it's actually very, very simple. And there's this fantastic metaphor that'll help us understand it here. So let's suppose that I have a mathematical statement, Sn. So what do I mean by that? I have a statement for S that is something different for each value of n. So for example, right, in the previous problem, it was 1 plus 3 plus ... 2n minus 1 equals n squared, right? That's a statement, and when n equals 7, it says something. When n equals 15, it says something. When n equals 12, it says something. It's like infinitely many statements, one for each n. So is the statement for, say, all n at least 1, and these are going to be natural numbers. I mean, this is a discrete math thing anyway, so these are going to be natural numbers here. Okay? But it also could be statements like some number depending on n is divisible by 16, or there's all sorts. We're going to see dozens of different examples of Sn statements there. Okay? So this is a potential a candidate Sn, this statement, this equality here. Okay? Now, in order to prove that statement, what mathematical induction says is you need to do two things, right? So Sn is true, and I'm just copying essentially what's on that slide, if the following two statements hold. The following two things can be proved, then Sn is true. Well, let me say Sn is true for all n, at least one, if the following hold. Number one, the slide says S1 holds. Okay, we'll get to that in just a moment, right? S1 is a specific instance of this. Does it work or does it not work? And two is, I don't know, how did I write this in the slide here? Sn minus 1, if Sn minus 1 is true, yeah. So actually, I'm going to say this just to keep it interesting. Sn minus 1 implies Sn. This is another way of phrasing exactly what's on that slide there. Sn minus 1 is some statement with an n minus 1 in it, and implies Sn means the truth of this follows from the truth of this. In other words, if I assume this to be true, can I establish this? Okay? So the statement Sn holds for everything if I can do two things. I can prove that it holds when n equals 1, and I can prove that it holds if I suppose the prior case. That's mathematical induction. Okay? And I'll justify why this makes sense, why this proves the whole thing with the metaphor, right, with these dominoes here. So imagine, I usually do a ladder metaphor because that's really nice, it's easier to draw, but I want to stick with the dominoes today. So let's imagine we have a bunch of dominoes. I need to have dominoes on the board, just like this. So I have this big row of dominoes that goes on forever. And let's let my statement Sn be the nth domino falls. Okay? So I'm claiming my statement here is that the nth domino in this list actually falls down. Now, for n equals 25, how would you prove this to me? Tip it over and wait, right? Anybody ever watch Domino Day on television? It's a little more popular in Europe. I forget what day of the year it is, but it's like they build these huge domino things and knock down the dominoes, and it's very fun to watch because it's just like completely wild. Anyway, some of those domino things take like many, many minutes to see everything fall. And so, yeah, the 10th one I can wait for it to fall. What about the billionth domino? I mean, you could still wait, but I want to prove every single one of them falls, so I can't wait long enough for that to happen, right? But instead, what if I told you the following? That I've got my row of dominoes, and I said to you, look, S1, the statement that the first domino falls, I can convince you of that. How do I convince you of that? I can literally just push the first domino over, and you're like, oh, okay, you can do that. And then what if I could also convince you that Sn minus 1 implies Sn? Let's think about that for a second. What is the meaning of that in the domino problem here? Sn minus 1 implies Sn. Exactly, right? So I'm looking at two consecutive dominoes. I'm asking, supposing this one falls, the next one falls, right? And that's something you would have to prove about the dominoes. Maybe someone told me that all of these infinitely many dominoes are placed, but I know that they're all half an inch apart. And then you're like, oh, okay, that means that the next one will always knock down, or the previous will always knock down the next, right? That'd be like the proof of that statement. But I wouldn't have to actually observe it on every single one if I knew that the previous knocks down the next, and I knew that the first fell. Think about what this says together, right? Using these two pieces of information without an actual experiment says what? Will the millionth domino fall? Yeah, because the first one falls, and then what does this say? For instance, what does it say about the second domino? It says the second domino falls, right? This works for every single n. So in when that's 2, I'm asking, does 1 imply 2? Yeah. Does 2 imply 3? Does 3 imply 4? Does 4 imply 5? And so on and so forth? Yes, this thing holds for all n. And so every single domino falls because the process starts and the process continues, essentially. That's the rough idea. You can turn this into a proof by contradiction if you like. I like the dominoes better. And one thing I want to emphasize here is both these cases are important. Right? Imagine for a second that your dominoes were in such a way that I could convince you the first domino falls, but you know, somewhere eventually at domino 115, there's a gap, right? Then what would be the issue here? Then part 2 would not hold, and this needs to hold always, and it doesn't hold here. And so yeah, the dominoes up until here fall, but everything else won't fall because this was not true. So you definitely need that. That's quite reasonable, right? The previous domino needs to knock down the next domino. But what is sort of interesting is that the first one is also absolutely crucial, right? Imagine I told you that one domino always knocks down the next domino. But what would the situation be like where the dominoes still don't fall despite that? Imagine the following hypothetical. My dominoes weigh 500 kilos or something like that, right? And I can convince you that, look, domino 17 will knock down domino 18, right? It's got a lot of momentum, it's huge, they're close, blah, blah, blah. But what about the first domino? Like, probably I can't push that over to get the process started. So even if the second step works, that I always know one domino knocks the next, if I can't get going, then I can't prove everything, okay? So these two steps are absolutely important to make things work. Maybe we'll see an example later. Yeah, we'll see some examples later when this is really relevant, okay? All right, so that's the model. Maybe I'll leave this up on the board for a little bit, and it's in the slide there, is that if I want to prove a statement is true for every single n, I need to show it holds for n equals 1, and then I need to show that the n case follows from the n minus 1 case here, okay? And frankly, like most of math, I think the best way to get a handle on this is, well, actually the best way is for you to solve a bunch of these problems, but that's not the format of this lecture. I'm going to solve a bunch of these problems, and if this is new for you, hopefully they'll become comfortable. If induction is old hat for you, then I promise by the end you'll see some hopefully you haven't seen before. Okay. All right, so maybe we can leave the slide up because I'm going to prove the one about the odd numbers real quick that was on the previous slide. I want to use it and show you what a proof looks like by induction here, how to make it a little bit more formal, okay? So let me write it as a theorem and say for all n at least 1, 1 plus 3 plus 5 plus 2n minus 1 equals n squared, right? That's the statement for the previous one that I sort of like roughly proved. And actually the things I went through are essentially the proof. Alec, did you have a question? You're just stretching. No. I said this one already, I have to say it because I'm wearing the t-shirt. So my advisor's advisor told us when that he was in seminar and they'd be eating, his advisor, this guy, who was teaching the classes would say, oh, I'm so glad that my lecture doesn't make you lose your appetite, right? Because I'm happy you're able to eat, Alec. Anyway. So, okay, I'd like to prove this one here, and I'm gonna put in red stuff that matches it back up to this format here, but the red stuff's not really technically part of the formal proof. It's just to give us a framework here. So this thing here, that's Sn, right? That's the statement Sn I want to show holds for everything here, okay? So how does induction work? Well, as I go through the examples today, I'm not going to be as careful as this, but usually the first line says the proof is by induction on, say, n, okay? N is the variable in question here. This is a way to indicate to your reader what kind of proof you're doing. If you just start without saying this, it's often confusing, okay? Now, if the proof is by induction, I'm using what's on that slide, the principle of induction, and I need to do these two things, right? I'm trying to show that holds for all n, which is what this thing says. And so I need to do step 1, and I need to do step 2, okay? These have names, and I'll say the names now because they'll come up when we give other proofs. This is usually the base case, right? This is the initializer here. Some people call it the anchor step. There's all sorts of different things. This is what starts the whole process. I need to check that S1 holds, okay? And I'll just write it like this. Those of you that have taken a proofs class with me know better, right? Proofs contain complete sentences, but you know, do as I say, not as I do in this case here. Actually, you can pretty much get away with this too. So what is the base case? That is the statement S1. I'll just put it here. We need to confirm whether the statement S1 holds or not. So what is the statement S1? This is the statement Sn. So S1 would be this thing here when I plug in a 1. Let's see if that's true. Usually it's very easy. So S1 says the sum of the first 1 many odds, it's just 1 on the left-hand side, should equal 1 squared. Are those things equal to each other? Yes, of course, right? So the base case is confirmed. S1 is true because the left-hand side of this would just be a single 1, right? You could plug it in there if you want. 2 times 1 minus 1 is 1. And it does equal n squared. Okay, so the base case is confirmed. I put a little check mark there. Okay, so now the hard part. I need to show that Sn minus 1 implies Sn. Okay? A best practice is to literally tell your reader what you're going to do here. So suppose the statement, meaning the statement of the theorem here, holds for n minus 1. Okay? And I'm going to write that down. It's not hard to keep it in your mind what the statement is, but it's nice to write it down. This is the free thing you get to do. This is what makes induction so powerful is I can use all the math that I know to do something by induction, plus I get this freebie here, Sn minus 1, which looks a lot like the thing I want to prove. It happens to be very helpful. So what is that? That's 1 plus 3 plus 5 plus all the way up to 2n minus 3. Right? We discussed this before, equals n minus 1 squared. Right? That's literally this statement here with Sn minus 1 instead of Sn. Okay, so suppose the statement holds for that. Now, so I'll even write this here. This is my Sn minus 1, right, this statement here. And what do I need to do to complete the proof by induction? I need to establish Sn using this information and whatever other math I want to use. Okay? So how do we do this? Well, that's Sn. I'd like to show that that's true. There's a few options here. Option 1 is to do what I did previously and make a substitution. Let me do that first. So Sn minus 1 looks like this on the left-hand side and this on the right-hand side. I can't write this out as being equal. I don't know it is equal. I'm trying to prove it. But let's write the left-hand side out first. 1 plus 3 plus 5 plus 2n minus 3 plus 2n minus 1, right? I've just written out, that's not even a mathematical statement, right? That's like a sentence fragment. I just wrote down a sum here. But now, the truth of Sn minus 1 allows me to do what with this? How can I simplify this dramatically? Normally I couldn't, but in induction I can. What simplification can I make? Yeah, this part, this whole run, all but the last term there is literally what's written here. And again, because we're working with induction, I've assumed this. I'm going to make a substitution there. So rewrite this as n minus 1 squared plus 2n minus 1. Right? So this thing here equals this here. And sometimes it's good to write, you know, afterwards that by the inductive hypothesis or by the assumption that I made, that's what I did here. I don't want to write it out, but that's what's happening. I'm using the truth of this. And then do you remember what happens to the right-hand side here? What does that simplify to? We did the arithmetic already prior. It comes out to n squared. Okay? And that's the end of the proof, right? By induction. Because what have I established? Using this, I've established that. Okay? So, you know, the full thing might be, therefore, by the principle of induction, you know, the proof is complete or blah, blah, blah. I will definitely not be doing that in our other examples here. And so I've established Sn from Sn minus 1, and I also got the base case there. Okay? All right. Nice. All right, so that's the first one. We'll do another one with some summations, but those get boring really quick. So the next one I think we can go on to while I erase here. That's definitely a QED, 100% QED, yeah. I won't give myself a QED for the dominoes proof. That's like not quite there, but. What's that? Yes, okay, I didn't realize I had made a slide for that. Yeah, the one that we just proved, but I wrote the statement there. Okay, now, I'll still, for the next couple examples, talk about Sn and so on, just to remind us what's going on, but after a few of these, we're just gonna have to get in the flow of these and, yeah. Okay, so, what do I wanna prove here? I have a chessboard, you can see it there. Let me draw one as well to help us out. And it has dimensions 2 to the n by 2 to the n. Right, so it could be 16 by 16. It could be 1024 by 1024. The dimensions of both are powers of 2. That's the only demand. And one of the squares is removed. I don't know, say here. That square is removed from it. Okay, so you might be curious how many squares are actually here. It's 2 to the n times 2 to the n minus 1, right? That's the number of squares that are present in this picture here. And it's a chessboard. I don't want to draw on the lines, but this is a big chessboard. And the claim is that we can tile with L-shaped, well, maybe I'll fill this one in, with these L-shaped dominoes. Okay, right? So there's a domino, and it has 3 rotations of it, right? It's shaped like that, and then it's shaped like that, and then it's shaped like that, maybe, and there's probably one more, right? Uh-oh. There. So I'm allowed to use those guys. I want to put those down. Yeah.
Duplicate the same ones.
Oh, did I? Yeah, I sure did. How about this? Yeah. Wait, first. Oh. Okay. Oh, all right. How about this? I think we know what I'm trying to get at here, right? I have the L tile. It clearly has 4 rotations. You're playing Tetris here. Yeah. So I've got this 4 versions of that L-shaped tile. And what I want to do, what I mean by tile, is I'm going to place them on the board here in such a way that first they're non-overlapping. I don't want 2 L shapes to be laying on top of each other, right? They should fit together nicely. I don't want them to go off the edge of the board. That's also ugly. And they shouldn't cover up the hole in the board either. Okay, so I just want to lay down the pieces. There's actually a board game. I can't remember what it is, but it's like Tetris from the top-down view almost, and you put these pieces together, and anyway, it's like exactly this. You're trying to tile as much as you want. And you can see in the statement there what I claim is that with these pieces here, I can use enough of them, I can perfectly color this picture here, okay? Let me do an example first because it's so nice. Let's try and tile the, say, 4x4 grid with the square removed using this and hope for the best, okay? So that's an instance of this, right? The theorem says the 4x4, 2 to the 2 by 2 to the 2 should be doable. So 1, 2, 3. There's a 4x4. And here's something really cool about the statement. It says it doesn't matter which square is removed. So I can remove any square I want, and each of those is actually a different statement, technically, right? Removing that is different than removing that, is different than removing that, is different than removing that. The theorem says it doesn't matter which one I remove, I can tile any one of them. Yeah, Alec?
Is this theorem specifically for only 3 cubed L's? Like we can't have like a 5 cubed L?
Right, that's a reasonable question to ask, but yeah, for now it's this shape and this shape only. Right, so even as the board grows, I'm still only getting these 3-piece ones. Actually, this raises something really interesting. A piece of size 3 covers how many squares on the board? 3. So if I'm able to do this tiling, what does it tell you about the number of squares on this board at the end? It's a multiple of 3, right? And actually, that's not immediately clear that that's even true, but it's not hard to see. Remember, in this specific instance, the number of squares to cover will be 4 times 4 minus 1, 15. That is a multiple of 3. And in general, power of 2 times same power of 2 minus 1 will always be divisible by 3. That doesn't mean it's possible, though, by the way. That just says if it's possible, that'll be the case, right? So let's remove, say, this one. Any one could be removed, and in fact, if I really wanted to prove the theorem for 4, I'd have to consider all the different possible ways of removing one here. I don't want to do that. I just want to see if I can tile this at once. Okay, so the way I usually do this is I just kind of go for it and hope for the best, right? Like there are algorithms, and in fact, the proof I'll give you will tell you how to write a program to solve this, but I don't want to do that yet. But we can see something immediately if we treat it like a puzzle, right? I'm going to have to put an L shape like that. This corner can't get covered any other way. So you do kind of get forced into some things. And now I'm just going to hope. Nope, see, already failed, right? Okay, that was bad. Usually I get away with this, but let's see what happens. How about, let's go here, because that one wasn't really good, and then, oh yeah, oh, we got it. Not that bad, right? Not that hard of a puzzle. Everybody see, I managed to do what I want. I covered it up. There's no overlapping L's. None of them go off the board. That's not covered. I used 1, 2, 3, 4, 5, which is exactly what we expect L's. Okay. Now this, I hope you're convinced that that's the same as removing this square instead, and this square and this square, right? I can rotate the board and get some. But if this was removed, something totally different would have to be done, okay? So the power of this statement really is that like it doesn't matter. Somehow I'm going to be able to tile the whole thing. So let's try and prove this by induction. And I'll talk about Sn still for this one here, okay? Yeah, so I'm going to write it as the 2 to the n cross 2 to the n minus a square can be tiled with these in the rotations. That's just the statement of the theorem here. Okay, so I'm going to call this Sn. Again, after probably this proof, I won't say Sn ever again, but this will just help us see what's going on by induction. Okay, so if I want to prove this statement holds for all n, induction says I have to do two things. I have to do a base case. Right, let's do that. So proof. Induction on n. The base case is quite lovely. What's the base case here? That's typically, although not always, when n equals 1. Later we'll do some examples when n isn't necessarily equal to 1. That's when n equals 1. Let's read out the statement of the theorem then. I have a 2 to the 1 by 2 to the 1 minus a square chessboard. What does that look like? That's a 2 to the 1 by 2 to the 1 board, right? 2 by 2 board. And one of the squares is removed. There's 4 options, but what do you all see? There, it's an L no matter what. Let's say that one's removed. Can this be tiled? The board literally is a tile that we're trying to tile with. So like it's super easy, put the L there, right? If that corner was removed, put the L there, blah, 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 blah. The point is the base case is covered here, right? It definitely works. Okay, so now assume statement for n minus 1. What is the statement for n minus 1? That says a 2 to the n minus 1 by 2 to the n minus 1 minus a square board can be tiled. Okay? This is my Sn minus 1 statement. Right? Sn minus 1, here I did S1, right? This is the justification of S1. Now I'm assuming Sn minus 1, and I want to prove Sn. And I really wish I hadn't written my statement right there, because this proof really benefits from a big picture. Well, I mean, this is big enough, right? So I'm trying to prove Sn. What does Sn say? It says that, well, it's written right here. It says a 2 to the n by 2 to the n minus a square board can be covered somehow. So this board is 2 to the n. Can you see this down here? I guess I can check. Yeah, that's just in, right? 2 to the n. And say the square is removed here. Now, it's very important here. Remember, I said this proof is going to work no matter where the square is removed. Here, I just made a specific placement. I hope when you see the rest of the proof, you'll believe me that it did not depend on the square being here, okay? And we'll get back to that in a moment, okay? So I'm claiming this one can be covered somehow. What I know is those that have dimensions half of this size in both dimension, they can be covered, okay? How can I turn a 2 to the n by 2 to the n board into a 2 to the n minus 1 by 2 to the n minus 1 board? What's a natural way to do that? Get rid of most of it. Yeah, that's exactly true. Yeah, let's like take a row and take a column. And which row and column are natural to do here? Why don't we split our board right down the middle, vertically and horizontally, okay? The arithmetic works out very nicely. This square here, the dimensions are now what? Well, they're 2 to the n divided by 2, which is 2 to the n minus 1 by 2 to the n minus 1. Right? And that's true for all these 4 pieces here. Now, does anybody see what I can do with induction? At least to get started? What do I know?
You know the bottom right one, it obviously holds 4.
Right, it's literally what's written here, right? 2 to the n minus 1 by 2 to the n minus 1 minus the square can be tiled somehow, right? I don't know how, but some way, my magic, that's the wonder of induction, right? Somehow it can be placed like this. But Alec, let me ask you, that tiled a quarter of the board. I need to somehow tile these, but at the moment, I can't use induction, right? Why?
Well, I was about to say the thing that's stressing me out is
Yeah.
I don't have a piece or a square removed from the other 3.
Exactly.
But the first thing that's popping into my head right now is that the way you've drawn it, it kind of looks like a piece.
Looks like a piece. Okay, that's actually really relevant, right? Actually here, you see a big L, which is a big L, right? Which is like part of it, right? And that absolutely. But Alec, if I may use your words, it's perfect. It's stressing you out that they're 2 to the n minus 1 by 2 to the n minus 1, but they're not missing a piece. And like, you can't tile them according to the statement of induction, right? It doesn't say a 2 to the n by 2 to the n can be tiled at the remove a square. But let's do this. Let me literally remove a square artificially for a moment. And very carefully, I'm going to remove that square. I'm going to remove that square. And I'm going to remove that square. Okay? I removed 3 very specific squares. What can I do here now? Induction, right? Induction says this can be tiled somehow. Right? I don't know how, but it's the same as this one. It doesn't matter that it's a corner removed rather than some random middle one. Remember, this is minus any square. This one also can be tiled by induction. And so can this one. And now, what have I at this moment failed to do though? Right, hold your breath. We haven't quite tiled the full thing. These 3 squares have not had a tile been put on them because this was done by induction and it got everything but that. Same with this, same with this. But that piece was very carefully chosen. It can just eat up one last tile. Right? Notice what's cool here. This produces a full tiling. Induction, 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 deterministic. Just place it down there specifically. Notice this tiling, 99% of the time, the tiles didn't reach across these boundaries, except for this one. But they're allowed to do that, right? We're certainly allowed to do that. That's the proof, right? No.
Okay that you fixed those 3 tiles?
Because remember, that's what's really crucial about the full statement here. It's not written out very cleanly here. It's on the slide there. That a 2 to the n by 2 to the n minus any square, right? Think of it, it's a suite of statements, right? It's this one with that corner removed versus that one, any one removed, including, which is useful for me, that specific one. So I'm very much relying, if it was about that one with a very specific square removed, then I wouldn't be able to make that choice there, right? I could also do something like this. I could say, oh, let's remove that one, and that one, right? Then I could tile this, this, and this, but then I'd be stuck. There's no way to cover up those last 3 there. So I was really careful to do it in such a way that I got those 3 there, because that's the tiles I had. If you have a different type of tiles, you might be able to figure out different types of things to do here, right? There's many other statements of this type that you can make, right? And one maybe thing you're thinking is, well, what if this piece was up in this corner here? Or what if it was up here instead? Well, then you just make the correct adjustment there. It was of no substance that it was here as opposed to anywhere else, because I only removed from these 3, okay? Good, I mean, I love that example. Notice, how many times do we use the inductive hypothesis here? 4 times, right? 1 here, 1 here, 1 here, 1 here, which was different than the previous where we just used it once. But that's something that helps emphasize is you get to use this thing for free, okay? And if you want to think about it for a little while, this actually basically produces an algorithm, right? I know how to cover a 2 by 2. If I want to cover a 4 by 4, what do I do according to this thing here? Right? Say it's a 4 by 4 with like this one removed. Well, split it in half, split it in half. That gets tiled by the base case. Then I remove this one, remove this one, remove this one, gets tiled by base case, tiled by base case, tiled. Now I've done a 4 by 4, right? And notice this was one specific 4 by 4. There's a way to do it depends on where that one's removed. What if I want to do an 8 by 8? Just run the algorithm on 4 of these, and you just keep iterating, and you get anything you want. Like, it's not hard to write a recursive program that will actually do this based on the base case and on this procedure here, okay? But outside of that, the statement's proved, because we did what induction requires. We checked it works to start, we assumed the previous case, and proved the next case, QED. Oh, okay, great. All right, so, interesting. I'm looking at the chat. That was definitely, I didn't know, that's cool. But what is interesting is how much time that took. So next is a summation one. Let's skip it. Let's go to this inequality here. Yeah. If there's time at the end, I can do some easy ones again. These aren't all going to get hard, but okay. I definitely want to get to some juicy ones because, you know, those early examples are great and they really help understand the method, but when we get to prove some really nice things with it, it gets fun. Okay, so here I want to prove this inequality, okay? So x is going to be a real number, Is there any condition on x? It's probably has to be, yeah, greater than -1, right? And then n is going to be a natural number. All that means is n equals 1, 2, 3, 4, 5, 6, just what we've been doing already here. And the claim, I'm just writing out what's on the slide again here, is that 1 plus x to the n is at least 1 plus nx. Did I get the order right of the inequality? Good. This is a really good example. You hear your teachers tell you this, is like, don't worry about the statement. If you can remember the proof that I do here, you'll just fix it at the end if you make a mistake here. This is the correct order here. Okay? So you can plug in values here, but what this is saying is that you can get a lower estimate on 1 over x raised to the nth power by just a linear factor of x, 1 plus n times x, okay? This actually in practice ends up being very useful in like, Hannah, can I ask you, someplace maybe you've seen this or used this before? Number theory comes up, or even probability theory, I was thinking, right? Like imagine you have a p probability here, or 1 minus p raised to the n, and you don't want to deal with that. This is a typical substitution there, okay? But its point now is to prove it by induction. Okay, so let's prove it by induction. The first thing I knew to do is a base case. Since the title of this section is induction, I'm not going to write induction at the beginning of my proofs anymore, okay? They're all by induction. So the base case, I need to check when n equals 1, whether or not this inequality holds or not. So for inequalities or equalities, just compute the left and the right-hand side and see, do they obey the rule that I'm hoping to establish? So the left-hand side is 1 plus x raised to the 1, and the right-hand side is 1 plus 1 times x. They're identical to each other, right? So it holds. Keep in mind, notice the way I wrote this, right? I checked the left, checked the right, and then saw that I have a greater than or equal to. But this holds when n equals 1. Great, so I can knock down the first domino. Okay, now assume the statement for n minus 1. Let's write that down specifically. What is the statement for n minus 1? Well, it is 1 plus x raised to the n minus 1 is at least 1 plus n minus 1 x. Is that okay? Right, that's the statement of this with n minus 1. And now I want to use this in whatever algebra I know to get this guy here, okay? So how might we do that? There's a few ways. Any suggestion from the audience? I want to show that this thing is true, and I'm allowed to use this thing here. Any ideas? You don't have to see all the way ahead. Okay, I like it a lot, right? This is something we didn't quite do yet in a previous example where instead of manipulating that into this is a true statement as far as I'm concerned. If I multiply both sides by 1 plus x, I'll get a new true statement. Actually, I'll let you guys think about why this is relevant, right? That will avoid, what do I not want to multiply an inequality by? 0, actually here I think I would just get away with 0, but but that's dangerous, definitely. A negative sign will flip the thing, I don't want to do that, right? But in this case, 1 plus x is greater than 0. It's positive, so it's safe to multiply both sides by it, okay? Actually, if you want, you can even, is that interesting to write it that way? Yeah, okay, that is interesting, but I'm not going to put it. Well, yeah, it is relevant, right? So x, 1 plus x is greater than 0, which means it's safe to multiply both sides by that. And Carter, why did you suggest that as opposed to anything else?
Because then you add 1 to the power.
Yeah, it'll transform this thing, 1 plus x to the n minus 1. It'll start to look like 1 plus x to the n. And that's like a good idea. It's not always clear that works, right? But that, like, trying to format this thing into that thing is my goal, essentially, right? So let's try that. Let's multiply both sides of this by 1 plus x. So I'll write it out. 1 plus x times 1 plus x to the n minus 1 is greater than or equal to 1 plus n minus 1 x 1 plus x. Okay, forgive me that I multiplied it on the left here and on the right there. Fortunately, multiplication is commutative, right? If you're, I don't know, Rohan, are you in algebra class now? You can't always do this, right? In some situations, like. Yeah, we're definitely super safe here. Yeah, absolutely, right? Okay, and so what does this simplify to, right? This gives me 1 plus x to the n. Excellent. And on the right-hand side, well, it's not clear exactly that that relates to this directly, but, well, it does, but the best thing to do here is like, let's just FOIL out and see what happens, right? If we're doing scratch work, that's what you would always do. So if we FOIL this out, we're gonna get a 1 plus x, and then an n minus 1x times 1, and then a n minus 1x squared. Are we comfortable with what I wrote there? Okay. And this is greater than or equal to, let's look here. I have a 1. What is x plus n minus 1x? nx, right? Right? These both have an x in them. That is n minus 1 of them. That has a 1, n minus 1x. And then what can you tell me about this term here? This is really nice here. It's greater than 0, or actually we don't even need greater. Greater than or equal to 0 would be just fine here. The point is this is positive, and it comes from two things. One, n is big enough. I mean, we already handled the case when n is 1. Here, actually, I didn't write it out, but we should assume that n is greater than 1, because we already know how to handle that. But moreover, very nicely, x squared, it's not even concerned about x being less than -1. If it's negative, it becomes positive. That's the key here. So what I did was just drop this positive term, or non-negative term, and then look what I got. This is greater than or equal to this, right? And this is, which is what I wanted, which is QED in disguise. You see, this was another strategy. Instead of doing a substitution, multiply both sides of a true equality or inequality by something else, do your algebra, hope for the best, okay? All right, that's a great one. All right, I'll erase and go to the next one. All right, I have no recollection. Oh, another inequality. Okay, great. Great. We'll use the same strategy for this one here. Manipulate some inequality and see what happens. Okay, so the statement is, in fact, the statement's on the slide. I'm not going to rewrite the full statement, but I will rewrite the inductive hypothesis. No, I'm going to make an interesting wrinkle here, because this will be occasionally helpful. Okay, how does induction go? Step 1, you need to show S1, right? Step 2, you need to show that the previous case implies the next case, that n minus 1 case implies the n case. But you can also do the following. You can go from Sn to Sn plus 1 if you want. It's just a change of variable name here to go from n to n plus 1. And I'm going to do that here, one, so that it adds it to our toolbox, but it's not a different technique. It's just, what's the term? Like typographically a little bit different, or computationally sometimes more convenient to go from n to n plus 1. But I hope that you all see that this is no different from going from n minus 1 to n. The only problem is the final statement that I get will not look like what's on the slide. It'll look like what's on the slide with n plus 1s instead. But that doesn't matter, right? This is a subroutine where I have to do this thing, independent of what the full statement looks like. And on this one, it makes it a little bit nicer, because here's the following. Oh, by the way, what's wrong with what I've written here for this specific problem? It's not wrong, but yeah. Yeah, we started our from n equals 2 here, so our base case is actually at n equals 2, not n equals 1. But in the domino model, this works just fine. This means from domino number 2, we start the process. Domino number 1 isn't a part of the question here, okay? I don't want to dwell on that anymore. I mean, normally this is half a class that we'd spend on this, but yeah, we start the base case somewhere. Okay, so let's check S2. S2 is the statement that, what do we have? 1 plus, 1 over the square root of 2. Okay, and so this should be greater than the square root of 2? Is that what the statement comes out? Okay, thanks, Hannah, yeah. Everybody okay with that? Like, that's what decodes there, that on the right you get root 2, yeah, and we get the first 2 terms there. Okay, this is, I'm going to put a question mark here. I often do this in my own work. I don't know that that's true yet. I have to establish this to establish the base case, right? This is the S2. S2. Let me ask you, is that true? Or how would you check whether that's true? Yeah, just use a calculator, right? Like, there are a few examples later where it's not nice. That's not the nice answer, right? Sometimes it's nice to not use a calculator. Here, it's good to just use a calculator. Actually, I think Also, it's not hard to see if you multiply both sides by root 2. So this statement is equivalent to, let's see what happens. Root 2 plus 1 greater than 2, right? That's what happens when I multiply both sides, and that's definitely true, right? Root 2, even if you don't have a calculator, what do you know about root 2? It's greater than 1. Something greater than 1 plus 1 is greater than 2. So if you don't want to use a calculator, that does also work. Okay, so now I want to use this model here and go from Sn to Sn plus 1. Okay? I do not want to write out the inductive hypothesis again because it's right there on the slide, right? That is the statement I'm going to assume, and I'm going to prove the next one. Okay? So the next one, let me write out the left-hand side of the next, no. Let's do what Carter suggested. I have what's on the slide there. What should I add to both sides to get closer to what I want? Any ideas? There's multiple answers to the question there. So what I want, we haven't formally stated what I want, but it's going to have n plus 1 terms on the right, and then on the left, it's very hard to keep oriented left and right on here, but, and then on the right is going to be root of n plus 1. Yeah, let's add 1 over root n plus 1 to both sides, okay? Now, I'm starting with a statement that's true, and I'm adding this to both sides, so we're going to have 1 plus 1 over root 2 plus 1 over root 3 plus 1 over root n plus, this is what I started with on the slide. I added this, and this thing here was greater than, is that the right direction? Yeah, I can see it over there. This is greater than 1 over root n, and I added this to both sides. Okay? Everybody agree with that? Traz, come on in. I mean, yeah. Right? So I had this is greater than this, and I added these to both sides. So this statement is still true here, right? But this is not what I'm trying to prove. What am I trying to prove? What do I want to see? This expression here, what I really would like to see there instead is, yeah, exactly, the square root of n plus 1. And so actually what this boils down to is this circled thing greater than that? Everybody see that if that were true, it would give me my chain. It would say that this is greater than this. That was for free from the inductive hypothesis. Is this greater than this? And so one thing you can do is just sit down and check that. But let me show you how to get it in a different way, because I think this is kind of nice. Let's take, so I'll say observe. The following observation will prove the inequality we want here, and then it'll prove the statement. So n times n plus 1 is certainly greater than n squared. I hope that's the right one. We'll see. If it doesn't work, we'll fix it here. That's certainly true, right? I mean, n are integers here. This one always holds here. How about we take the square root of both sides? See what happens, right? That introduces square roots of things we're definitely interested in. So then I get root n times root n plus 1 is greater than n. That okay? Square root of both sides. And now, I don't like what I'm seeing here. Okay, nice. I like it. Let's add 1 to both sides. Awesome. Do I want to add 1 now or before? No, I like it. That? Let's see what happens. Yeah. Okay, great. Now, this, everyone okay with this? This was true. I took the square root of both sides, still true. Added 1 to both sides, still true. That's the hack. Who said add 1? Yeah, Carter, great. Okay, that's fantastic. Now let's try and simplify this by dividing both sides by root n plus 1. The whole thing has to be divided by. That's crucial. That's the purpose of the n plus 1. Now this is still true. Let's simplify and watch the magic here. This is what happens on the right-hand side. That's the easier side. N plus 1 divided by root n plus 1 leaves what? Yeah, root n plus 1 in the numerator. And on the left-hand side, we get root n times root n plus 1 over root n plus 1. That just leaves a root n. And then we have 1 over root n plus 1. That's what we wanted, right? I was hoping to show this. I didn't write the inequality here. I was hoping to show that. That's exactly what's here. Right? Isn't that cute? Just comes from this like completely trivial thing. And the right order of operations. but that gives you the thing here, right? And you could say, well, why do you plug that in? Like this statement here is stronger, right? Why not just use that? And there's a problem though. Where did that statement come from? It came from induction hypothesis, but you can only use, with induction you have to go from n to the statement for n plus 1. This is not the statement for n plus 1. This is something else. It's not even actually clear that that circled thing is true. It follows from the assumption on the slide there, but that slide, we don't know that that's true yet until we've gone through this. Okay, that was maybe not a helpful aside, but we did get what we wanted, right? We got this thing is greater than this thing, and that is the exact statement Sn plus 1. And so that followed from Sn. And so we've done the two things that induction require, and the theorem's proved. Okay? All right, excellent. All right, maybe there's some non-algebra one next. That's what yeah. Okay, good. There's definitely algebra here still, but the wrinkle of like the way it works is fun. QED, I'll get QED. Thank you. 4 QEDs. I'm lucky too. Every one of my slides has a QED, I think. Well, Molly had 14, so I don't know if I can get quite as many. Definitely. Okay. So, problem here, we have lines drawn in the plane. More or less randomly, but randomly has a very specific meaning here. They're in what we call as general position, and that means two things. One, it's written in the statement there, we're not allowed to have two parallel lines. We want all of our lines to intersect, otherwise we aren't able to get a formula. Moreover, we don't want to allow 3 or more lines to meet at a single point too. That can happen in general, but that causes us a headache in this thing here. Once I've drawn those lines, in this case I have what, 4 lines? Yeah, 4 lines here that all intersect and no 3 in a point. Then I want to count how many regions does this create. Okay? So how many regions? I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think I got them all there, right? There's 11, I hope. There's these unbounded regions, right? These regions don't overlap. The lines go off to infinity here, okay? And what the formula claims here is that if I do this, I always get n squared plus 2n plus 2 over 2. Actually, I don't know what the formula is. I got it right? Oh, all right. N on top here, plus n. Okay, yeah, good. So apparently the formula is that, all right? Let's just check against this case real quick. So here I had what, how many lines did we have? Or, no, there were just 4 lines here, yeah? 5 lines. How many? 1, 2, 4, just 4 lines here. What happens when we plug them into this? 16, 20, 22 over 2, 11. Ah, okay, it matched, right? Doesn't prove anything, but it does match. Okay, so I want to prove this statement by induction, that this formula holds for these guys here. What's our base case? There's a little bit of wiggle room here, actually. You could do 0 lines, actually. The formula, let's check that the formula holds. If it doesn't hold for 0 lines, then nothing works, but it will actually hold. Yeah, great suggestion. We've started with n equals 1 all the time here. You don't have to. You can hold with whatever the formula works for. We'll also check n equals 1 just because it's good practice. So when n equals 0, I have no lines. They automatically satisfy these rules, fine. How many regions do you get? Yeah, you just get the plane. And this formula, I believe, works, right? You get 0 plus 2 over 2, you get 1. So actually the base case works. You don't need to do a second base case, although later we'll see sometimes you do. Let's just see what would happen if there was 1 line. You have 1 line, how many regions do you get? 2, one side, other side. And no surprise, right? 1 plus 2 over 2, you get 2. So that one holds as well, okay? I didn't write out the formula, but that's what we're checking, is that it works. Okay, so now what we're gonna say is, let's go from n minus 1 lines to n lines. But we could go from n lines to n plus 1 lines, whatever we want, but I think this one's a little bit nicer. So let's assume that n minus 1 lines gives us n minus 1 squared plus n minus 1 plus 2 over 2 regions. Okay? Think about how powerful this assumption is, right? I'm saying no matter how I put down n minus 1 lines, as long as they obey these 2 rules, no matter what, they give me that many regions. But that's the inductive hypothesis. I just have to show that this formula holds when I have n lines, okay? And here's how this one works. Suppose I have n lines is drawn in the plane, right, somehow. And I remove one of the lines. What can you tell me now? I have n minus 1 lines, and those create this amount of regions here. So let me think now about putting that nth line back down. Okay, so I'm going to draw it like literally draw it mechanically here. Let's imagine, and we'll use an example here, but I hope that you'll believe me in the argument here. Let's draw that line. Now, when I draw this line, it starts somewhere at infinity. And we know that it obeys these two rules. So it's not parallel to any of those lines. So I need it to intersect all of them. So I have to be careful. I may draw poorly here. We're going to cross our fingers. It also should never pass through an existing intersection. If I do that, that's always easy to fix, though. You can like adjust your line by a millionth of a degree. It doesn't change other things. But let's see if we can get a line here that hits everything. Okay, what if okay, I was going to be really cavalier, but. Okay, I mean, this will work, right? Like eventually crosses this one here, right? Maybe I'll add to that. Did that cross all the existing lines? I think it did, right? So it crosses all the existing lines, and it never intersected in a triple position here, right? Did he get them all, Trez? It's one. Yeah, it's nice when there's like a bundle that are like somewhat vertical, and I just have to like get those. But yeah, okay. So let's make an important observation. That's an observation about geometry, and I hope you believe that it's not really dependent on this specific picture. Let's walk along this line here, and I actually like to think of this as like you have this huge ranch that's partitioned up into these different pieces, and I'm building a new fence, and I want to create new regions here. I want to see how many get created. So I started at an infinity here. I'm walking along. When I hit the first fence, what happens? Yeah, some existing region number 5 in this picture, is now split in two, right? It started from infinity, hit this thing here, and now these two sides are split off from each other. So I'm going to just write +1 region there when I reach that position. Now, I hop over this fence, keep building my fence, and eventually what happens? I reach another fence. And that also creates a new region, right? It may not be a small, it's hard to tell, maybe if I had written my number 1 over here, then it'd be +1 down here. But that's just a naming convention. What happens is I cross this territory and reach this fence here. I create another region. And then here, this long one here, created another region, right? Between two fences, you walk along the line, that literally just splits the region in two pieces. Maybe not even pieces, but two pieces. And then the very last point, this is a little interesting. I'm in now pasture number 2, and there's no other fence to reach, but I go off to infinity, and that actually splits it into another one as well there, okay? Now let's try and analyze what happened here. I created a new region every time what happened? Yeah, each time I reached a fence +1, right? There's like an infinite fence as well that kind of, so it's one more, right? Let's see, +1, +2, +3, +4, and then +5, and infinity there, okay? In this case here, how many regions am I now adding? Is it, yeah, let's see, is it? Yeah, right, okay, but the nth line, I think created n regions, right? Yeah, so say it this way, n minus 1 plus 1, right? Yeah, it was what you're reasoning, yeah. So that means that if n minus 1 lines gives me this many regions, how many regions are created with the n lines according to that assumption there? Or how many are there in total? It's this quantity plus n, right? And so let's write that out. Maybe I won't use the blue. And I don't know how badly I want to do the arithmetic here, but not that it's hard or anything, it's just +2/2 plus n new regions, right? What do we anticipate about this expression here? Yeah, it should simplify into this here. That would prove my theorem. I don't know, should we do it? I don't hear any, I mean, like, this is, the algebra isn't the most fun part. However, it is very satisfying when this like clicks into this one here, and there'll be some even more satisfying ones, but maybe let's do this one real quick. So I would FOIL out and hope for the best here. So n squared minus 2n plus 1 plus n minus 1 plus 2 over 2 plus 2n over 2. Yeah? This cancels with this. This cancels with this. Ah, we got it, right? N squared plus n plus 2 over 2. We got it there. That proves it, right? And do you all agree that the picture really wasn't what was going on, right? It was this walk across a pasture creates a new one. But the thing is, if you have these n lines placed, pull one off, apply induction to the n minus 1 lines, put the line back, see how many you actually have, you get the answer. Okay, all right. Great, what's next? No worries. No worries. And I'm gonna have to make some decisions here too, because I probably can't get all through all these. Okay. Yeah, there's about this, this much. Yeah, okay, I'll be careful with that. Okay, this one is really nice. I want to do this one. I'll do half of this one. I'll do the upper bound, okay? So this is really interesting, right? We run into the factorial expression, and it's hard to estimate. Like, how does the factorial grow? It grows faster than exponential functions, which is a typical thing to learn here. But notice here it's bounded between these n to the n functions here. And so this says roughly that its behavior is about an n over e to the n. You can see they're offset by an n term. That plot of them is a log plot if you see the axis there. But it behaves really nicely between them. And if you're really knowledgeable here, that's not the plot of n factorial. Why is that not the plot of n factorial? Yeah, there should be just dots. You can estimate, but there's a gamma function that works for all real numbers as well. That's technically what's going on here, but I don't want to prove it for the gamma function because I want to use induction on the discrete values there. But let's prove the upper bound at least, right? So the upper bound is that n factorial is at most n over e to the n, right? Lower bound is a similar argument. Okay, so how do we prove this? Well, I'll just talk out the base case. When n equals 1, you have 1 factorial on the left, and on the right you have 1 times e over 1 over e to the 1. The e's cancel. You have 1 as most 1. Base case works perfectly. Okay, so now I would like to establish that, and I'm going to assume the obvious inductive hypothesis, which is just n minus 1's plugged in for everything there. Okay, so I'll use that in a moment. So if I want to show n factorial is at most this, here's where I would start. Write n factorial, and how should I rewrite n factorial to have a clear opportunity to use the inductive hypothesis? Almost, yeah, not quite, right? The inductive hypothesis will be about what? It'll be an upper bound on n minus 1 factorial. So if I can isolate an n minus 1 factorial, I can plug something in for that, right? Yeah, exactly. N times n minus 1 factorial. That's another way of writing out n factorial, right? Simple substitution. Now, by induction, that is at most n, that's just that n, times my upper bound on that thing there, right? Which is something of this in terms of n minus 1. Let's plug that in. And then it's a little bit scary, to be honest. N minus 1 times e, n minus 1 over e to the n minus 1. Everybody okay? That was the substitution of this. I replaced with its upper bound, which I know exists by induction. I haven't written out all the formal stuff, but that's what induction says. And this sort of fits our strategy before, is like replace this with something that I can, get closer to the end. And this thing vaguely resembles this, but here it's a little dismaying, right? Like the exponent is different, which is usually not a problem, right? It's easy to change one exponent to the other as long as what? As long as the bases are like the same. But how am I going to transform an n minus 1 to the n minus 1 into an n to the n, right? They're not totally different functions, but one isn't clearly bigger than the other. Like it's not obvious. Well, I guess n to the n is bigger than n minus 1 to the n minus 1, but actually that's a problem. That's not a problem necessarily, but I can't make a simple substitution here. I want to transform this into this. So here's what I'm going to do. Shout out to Cameron, who taught me this expression. I'm going to multiply this expression here by 1, by a fancy 1, is how she liked to call it here, okay? This, if you multiply something by 1, it doesn't change it. So I'm going to multiply by a very particular 1. I'm going to multiply this by n over e to the n times e over n to the n. Everybody agree that I didn't do anything here, right? And why is this useful? Well, I mean, it's mostly useful because it works, but notice that's good, right? I want to see that thing there because that's what I'm hoping to establish here. So seeing that's good, but I have all this other mess. But let's clean things up. There's some cancellation going on. So let's pull out these things here that I'm hoping to have by themselves, right? Those are the things I expect. So this equals, I get n. I'll put a little, I did this in my notes. I think it's helpful. I'm going to put a little check mark just to bookkeep here. Took care of that. Times e. Took care of that. And then n over e to the n. Took care of that. And that's that thing there, right? But I have some stuff left over. I have, well, look at this. I have n minus 1 times n minus 1 to the n minus 1. That's fine, right? That's n minus 1 to the n. That's fine, yeah. And how about this? I have 1 over n to the n. That's that n. And I have n minus 1 to the n. So this expression to the n. So that takes care of this and this. And not quite everything. I took care of the n to the n here. What is missing? What haven't I not? Yeah, these check marks are, I have to be really careful with. This e to the n minus 1 is still hanging around, and so is this e to the n is still hanging around, right? So what's actually left? A single e, right? This e got pulled out front here. So I mean, technically there's an e squared, but this is what's left over. Okay? This is what I want. This is what I have here. What would be sufficient to prove the theorem? Right? I have n factorial. I want to show it's at most that expression alone. I know that it's at most that expression times something here. What can I learn about this to finish the proof? If that is, yeah, 1 or less, right? If this is 1 or less, if it's 1, then this thing is at most that thing. No problem. If this is less than 1, then this is actually strictly less than this because of the multiply by less than 1. So that only helps me if it's less than 1. So the question is this expression less than 1? Everybody okay with that? Or is it at most 1? So let's examine it. I'll just write it down again here, because I really want you to look at the first part of the expression there. Anybody recognize that? Yeah, as the limit of this is actually not, it's not e actually, it's 1 over e, which is really would be great, right? Because if this is 1 over e times e, we get 1 here. Unfortunately, it's the limit, right? So it's not equal to it. However, if you analyze the limit and understand how it approaches it, it works. But I'm going to add a little bonus thing here that gives it to us even easier. So here's a fact I want to tell you. We're not going to prove this. Well, it's not hard to prove, though. Is e to the x and 1 plus x have a very important relationship with one another here. Esmail, do you remember the relationship? What's that, Prince? Yeah, close to, yeah, they're actually, yeah, that's even stronger than what I want here. But you're right, if you okay, the battery's out, that's fine. So that one, you put it on there, and then this one goes here.
It's working again.
What? Wait, Oh, that's okay.
It
That's
must be coming with this one.
Yeah.
it's because I turned it back on and it's flashing desperately that it's running out of batteries.
Oh,
So I
okay.
just like,
Okay.
Michael, I put that one. It just saved us a moment. so.
Okay. Do you want me to plug this one in then?
Yeah, start charging
Okay.
it if you would.
And then
But then we'll have you test again.
okay. Yeah.
Yeah. The camera's, it says it's obstructed. External mic will partially obstruct. Oh. Yeah, just hit OK. Okay, so I think you guys can hear me. Santa, that's why it came back. That's literally what I did, was turn it back on again. But I think, it's when something dies and the battery goes off and you like turn it back on, like it works until it just dies again. So now we're on the other mic. You were hearing? Okay, great. Okay, where were we? Oh, I was getting another great punchline. I don't know how much of the chat lost here. But this fact should be bolded and put in fluorescent letters. It's super, super, super valuable. Good thing to memorize, good thing to use. Let's use it here, okay? So let me rewrite the following. And one of the reasons, Traz was explaining about the behavior of the limit, that's baked into this thing here as well. So let's rewrite this expression. I want to get it less than 1. So this is instead 1 minus 1 over n to the n e, right? But now according to this thing here, and what's lovely about this fact is it doesn't care whether x is negative or positive or anything. X is negative 1 over n. So this is less than e to the negative 1 over n, right? Negative 1 over n is there, and now that's my x, and now that's my x there. And that expression is raised to the n. That's that n in there. And then it's times e. But look what I have here, right? This is e to the negative 1 times e, that's 1. And so I got what I wanted, that this leftover stuff here it's actually strictly less than 1, but at most 1 was sufficient to prove the theorem there, right? That's a really nice one. You don't need to use this again. You can use a little calculus and know the behavior of this, but it's a nice substitution. The lower bound is similar. You use this inequality as well. You have to be a little trickier. Maybe it's a good homework, okay? All right, yeah, you can go on to the next one. And we do it on time. 122, okay. That probably didn't advance the slide, right? I know why though. Yeah, I know why though. All right, hit it again. Great, okay, oh, this one's sweet. This is a really good instance of base case being harder than inductive step, right? So far, the base cases were all like, just plug in 1 and check, or plug in 2 and check, and blah, blah, blah. This one, the base case is the real meat of the problem. So let's try and understand what this one is saying here, right? I'm going to write a few things out. So suppose I have functions f1, f2, fn, or n, yeah, n of them. Say they're real valued functions and they're continuous, right? So they go, I don't know. Yeah, let's just say they're from the reals or something like that, right? Continuous. All right, and there's a formal definition of what continuous is, and we won't actually use it directly, but I will ask you guys a couple things. I hope many of you have seen some calculus or maybe some real analysis. And now I'm going to construct a new function, right, which is the following. For now, I'll call it m sub n of x, right? So each of these functions takes an x value, and m sub n of x does the following. It just computes every single one of those functions on x, and then spits out their minimum. That's the function, okay? So actually in our picture there, I hope maybe I can redraw it. The picture had, what, a linear function, some cubic, and then parabola, maybe. It doesn't matter, right? Like, so there's my example. There's my 3 functions, but you could have as many functions as you like. The minimum function we can draw in the picture here, right? Starting at negative infinity, what's the minimum value of this function the whole time? It's the linear function here, right? So I'll just sort of trace it here, right? If I look at all 3 functions, the cubic function's way up here, the quadratic's way even higher up because of the particulars there. The linear one's like losing for the whole beginning part. Then I hit the cubic here, and the loser is the cubic, right? That's the lowest of the 3 functions there. And then this is the lowest of the function here. And then back up to here. And then that's still the lowest. And then the cubic, no surprise here, right? Obviously, cubic's going to be the losing function eventually here. Right? So that red line, that's the plot of my function. That function, I claim, is continuous. From looking at it, yeah, that's continuous, right? Although, what can you tell me about, like, say, its second derivative? Right? There's some problems. It has what are these points called again? In calculus, where there's like these funny breakpoints where, you know, you're not going to be able to compute the, oh, wait, you can't take the derivative of those points, right? Yeah, you can't take the first derivative, forget the second derivative, right? Yeah, because the limits don't, yeah, the slopes don't match up at that point. It's there's a word for it. No? A not continuous point. Well, it's continuous, not differentiable. Anyway, someone in the chat will surely say what it is. But I claim that this function, regardless of what these are, as long as they're continuous, this new minimum function is continuous. Okay? All right. And it's not terribly surprising here by looking at the picture, but you know, that's not a proof, not even close, right? So, okay, let's figure out how to prove this. So, my base case, actually, this is interesting. So, actually, what base case could I get away with here in principle? Yeah, if I do one graph, say M1, where I'm just looking at the minimum of the first function on x, what is that function? It's the function itself, and that is actually continuous. That does work as a base case. However, for the proof, we're going to need the two-function case to get the proof to work. But this is really astute that actually the base case, we don't need to do the two-function version for a base case. But we'll see in a moment that the two-function version is needed to get the proof to work. So we'll just start there. Moreover, I think it's reasonable to say that the statement of the theorem for one function is not especially interesting, right? A continuous function is continuous. But okay, but we should exploit easiness when we can, but anyway. Okay, so a corner. Corner, yeah, that's as good as anything, so. All right, let's take a look at this. And there's some analysis going on here that I'm going to hand wave a little bit. I'm actually going to ask you all. So base case n equals 1 is just fine, but I'm going to do the n equals 2 because that's interesting anyway. So let's look at the two-function version. So that says, and I'm going to call it M2, say, is the minimum function fx1, fx2. Right, so you've got two functions, f and g, or f1, g2, or f1, g1. And you just, at every single x, you look at the two functions, take the smaller of the two values, and that, I claim, is continuous. Okay, so the way to do this is to rewrite mx not as this minimum function, but I want to rewrite it as a function that's much clearer that it's continuous here. And this is this amazing trick. You do the following here. And I hope I get it right, but we'll work it out here. I'm going to consider the following function. 1/2 f1 of x plus f2 of x minus the absolute value of f1 of x plus f2 of x. Uh-oh. I literally don't remember. But okay, well, this part's not hard. We'll just check if this is true or not. If it's not, we'll adapt it so that it is. Okay? Let's think about this for a second. So if I'm looking at a specific value x, one of these two functions gets the minimum, or maybe both achieve the minimum at the same time. Let's see if this way of determining the minimum is the same as what happens here. So let's look at a specific x value real quick. And there's two cases, but let's imagine that f1 of x is less than or equal to f2 of x, right? It's either f1 of x is at most f2 or the other way around. Right? Let's see what happens in this case. In this case, what should this minimum function return? Yeah, f1 of x, because that's the minimum of the two values there. Or, I mean, they're equal to each other there. What does this crazy function return? Let's look at it. It returns f1 of x plus f2 of x here. Those are two totally different values. f2 might be way bigger than f1. And then it subtracts from it, I think this is a minus. It subtracts from them what? Look at these two here. f1 of x minus f2 of x is the difference between the two, and it'll be negative actually in this case because f2 was the bigger. But in this case, what will end up being subtracted here, it'll be f2 plus f1, right? We have to analyze the absolute value sign here to get this right. You know what? Let's do this instead. The other one's fine, but this one's like easy. We don't have to do a flip. We do have to check both, but if you see this one, you'll believe me. Okay, so say F1 is the winner. Then what gets returned? You return the value of F1, the value of F2, and then minus what happens to this thing here. What happens to the absolute value signs in this case here? They go away, right? It's F1 is bigger than F2, the absolute value signs disappear, and so I actually have 1/2 F1x plus F2x minus F1x minus F2x, right? And what happens here, the F1x and F1x cancel with each other, and the F2x and F2x add, it's negative, negative, and there's a 1/2, so this spits out F2x. What does the minimum function spit out? F2x, right? So at least in this case, it does what it's supposed to do. And the other case is the same thing, it's just that when F2 wins, these get flipped around when you remove the absolute value sign, and things cancel out exactly as they should. Okay? So what it means is this minimum function, I've simulated with this other crazier function, right? That's actually M2x. And why is that interesting? That's interesting because I'm going to ask you the following questions. Those are continuous function. What can you tell me about their sum? Yeah, I'm not going to prove that to you. That's something you probably see this in Calc 1 even, right? And you might prove it in real analysis or something like that. Maybe even prove it in Calc 1. The sum of continuous functions, that's continuous, no problem there. So this one's continuous. What about inside the absolute value signs? I have the difference of two continuous functions. Yeah, it's the same thing, right? What about the absolute value of a continuous function? Also, thumbs up, exactly. You can visualize it that it's continuous, but it also can be proved. So this is continuous. I know I'm getting pedantic here. Now, you have a continuous function minus a continuous function. That's continuous. And I know this is absurd, but I have 1/2 times the continuous function. Right, we're okay. So, the minimum for two functions is continuous, okay? Now, of course, that technically is a difficult base case because like that required a lot of like analysis, which we use those as theorems as we're known. But notice we're not talking about the minimum anymore, right? Maybe, I'm sure this can be proved directly, but this is a really nice way of applying a bunch of things. And you might wonder, and actually I'm literally wondering now, if there's some hack to turn 3 functions, 4 functions, n functions into some weird minimums and stuff. I bet there is, but I don't want to try and figure that out. I want to prove it by induction instead, okay? And the induction's amazing. So let's do this. All right, so now what do we know? We know it works for 2 functions, that m2x is continuous, or if we look at the minimum of 2 functions, continuous functions, it's continuous. And I'd like to, let's assume this time and show that it works for n plus 1 functions. Okay, so I give you the functions f1, x, f2, x, fn, x, fn plus 1, x. And I tell you these are all continuous. And I'm interested in the minimum of those functions. Right, so this is, I'll call this m n plus 1, x. Is that function continuous here? Okay. Well, what can I do? I don't know anything about the minimum of n plus 1 functions. I do know something about the minimum of n functions, and I do know something about the minimum of 2 functions. Any suggestions here? Yeah. Both of you go ahead. Okay. Carter, and then of that block, and then, yeah, were you thinking the same thing? Great, so let's write that. So let's say this is the same as taking the minimum of f1x up to fnx minimum, and then fn plus 1x. Right? I've just rewritten it. And actually, in some instances, you have to be careful about minimums of minimums or maximum minimums in different order might be troublesome. But if we're thinking about functions here, taking the minimum in this way is perfectly fine, right? Because all it's saying is like, oh, find the smallest of those first and then compare it against this one, the end result will be, of course, the minimum in this list, right? If that's the absolute smallest, then it beats everything in here after you found the smallest, and vice versa. If the smallest one is in here, then the comparison against that at the end doesn't do anything there. So I've just transformed this minimum into this one, and then what do we have here? Well, this is the function that is the minimum of n functions, which is continuous by the inductive hypothesis. This is continuous. And this function, by assumption, is also continuous. And now I'm asking, is the minimum of two continuous functions continuous? And that was, interestingly enough, my base case. You actually used the base case. Kind of, right? I kind of cheated. I could have gotten away with the base case. But you see, I would have had to prove this anyway, because I'm using it there for 2. Right? So those are continuous, so the whole thing is continuous. Right? I think these are my favorite inductions, where the base case is not easy, and where you kind of use the base case in the proof of the full thing. Because we also use the inductive hypothesis. Right? We also use that this was continuous in this part, and then that's a function that's continuous, and you have the thing of both. So once you see to do it that way, it works really good. Is this for arbitrary functions, was asked. That's a good question. Arbitrary continuous real valued functions, I think, right? So, okay.
You've missed like 3 QEDs.
3 QEDs. 1, 2, 3. All right. All right. What do we got there? We got the De Morgan's one. Okay, this one I got to do because it's like so satisfying to walk through it. I'll just do part of it. Okay. If you're not familiar with logic, then you know it won't be the easiest. Okay. Maybe I'll do the one on the proof's kind of immediate. Yes, it probably is. I mean, it is immediate anyway. So, okay. So we're given the following, that the negation of the, I don't know, what are these, literals? I forget the name of these things. And which one do I do? The and? Yeah, P and Q is, well, it's on the slide there, but Jose, you remember it? You're still here, right? I taught you this in the class, right? We went through this. I mean, I'm just kidding. I'll ask a follow-up question, but it's you not the P and then or and then not Q. Not the proof, but do you remember what we had to do to prove this? Yeah, I mean, you remember there was a special name for the type of thing we did to prove it. But you're right, you do prove equivalence and so on. It's an alliteration. Anyone remember? It's a truth table. Oh. Yeah, right. So you list out all the truth values of this and then match the truth values of this and so on. If you're not familiar with this Boolean logic, I don't want to dwell on it too much. The point is this is true. And from here on, we can prove the theorem with just like symbol manipulation. We don't need to know anything. Okay? So what do I want to prove? I want to show the following. I want to show that the not of the multi-and pi, I ranges from 1 up to n, right? That's a replacement for what's up here. Not of p1 and p2 and p3 and p4 and p5. That's the way of expressing this. You know your sigma notation, your product notation, this one works here. I want to show that this is equivalent to, well, what does this one look like? It's a big or, I equals 1 up to n, over the nots of all those pi's, okay? That is the n-term version of that one there, okay? When n equals 2, this expression here is literally what's written up here, right? Because think about what it says. This says for I ranges from 1 up to 2, I'm looking at P1 and P2, or I can rename them P and Q if I want, negating them and asking, is that equivalent to not P1 or not P2? That's what's written right there, right? So this is given to us, right? And we didn't prove it directly, but it's proved by truth tables, right? You can check through it there, okay? Now, the idea is almost the same as in the previous one. Let's assume that this statement holds for n minus 1. So if I have an n minus 1 here and an n minus 1 here, I can use that expression. And I'm going to try and prove this now. So let's prove it in the following way, right? And I equals 1 up to n pi. And this is equivalent to, and there's no logic here, I'm just fiddling with symbols here, what I'm going to do is, of this is P1 and P2 and P3 and P4 and P4 and P6 and so on. I'm going to strip off the Pn. Well, let's get the negation out front still. Pn, right? ANDed with the big AND, I equals 1 up to the remaining Pi. That. I claim that this isn't like, there's no logic here, it's just a symbol thing. This is the AND of P1, P2, P3, P4, P5 up to Pn. This is just pulling the Pn out front and taking the AND of P1, P2, P3, P4 all the way up to Pn minus 1. The one thing I guess there is a bit of logic is that these AND operators are commutative, right? This N was at the end of this one, I can pull it out front there. This notation's really dangerous to do. If your operator is not commutative, then it's not always clear what's going on, although you can get away with it. Okay, so now what's nice about this, now I can apply this rule to the expression here. Let me circle them. What do I have? I have P and Q, right? The AND of all these things is still just a literal here. I forget the name of these damn things. They have some special name, but putting them together, it's just a compound one. And so what does that say? So by the base case, let's apply this to it. I get not Pn or not of this big circled thing, and I equals 1 up to n minus 1 Pi. Right? That okay with everybody? That P and Q, not P and Q is not P or not Q. Okay? And now we're almost done. I have not P, N, or this, maybe I'll put in extra parentheses here just to really drive it home there. I have the not of the AND of the PIs. It's not written up here, but what's the inductive hypothesis? It's literally that, right? It would be this with an n minus 1, I to n minus 1 of Pi knotted. That's I to n minus 1 Pi knotted. So I should be able to write this with an n minus 1 instead. So then this becomes an or, I equals 1 up to n minus 1 P not Pi. And then the final step is, look what I have. I have not Pn or not all the other Pis. That can just be pulled into a single or not Pi, I from 1 up to n. And I have this chain, this thing here equals this thing here, which is what I was trying to establish. Notice how similar it is to the previous one, right? We use the inductive hypothesis and we use the base case as well along the way, right? This first step, well, this was nothing. This step here was the base case, and then this step here was the inductive hypothesis, and then we just merged terms there. Okay. Good. Okay. Yeah, the chicken nugget theorem's next. I got to do it. It's just too good to not do. It's my favorite. Oh, sweet. Yes. Good. We can like, what do they call it? Yeah, okay, I know what it is. So you know, this event was inspired by speed running. You know, people speed run on Twitch, video games and stuff. I'm very fascinated by it. And when you retime something, right? If you set a world record and you're not like sure if you got it, they go back and retime it and do it really formally. We can retime the QEDs and make sure, like by watching the VOD of like how many did I get, and so we'll get the correct number at the end. Or so. Yeah, well, you know, I think actually if we go through the slides and just count the ones I did, we could probably do it really quickly. Sure. Okay. Okay. 144. I can't remember what's next, so I'll cover this one and then maybe we'll have to make some decisions because there's a couple theorems at the end I really absolutely want to prove. So, what's that? No, it's okay. It's okay. Yeah, it'll come to me. Okay, chicken nugget theorem. So we go to McDonald's, and they used to be like this, and I don't think they are anymore, but we get boxes of chicken nuggets that have 6 pieces, 20 pieces. Oh, I don't know why I did it that way. 9 pieces and 20 pieces. And of course, the natural question is, how many different amounts can I make, right? with these box sizes, you can't make 19 nuggets. Just sit down and think about it like you can't put them together to get 19. But you can get 18, right? You can take 2 9s, you can take 3 6s, for instance. I don't think you can get 21. There's some numbers you can get, some numbers you can't get. You can sit down for a long time and find that up to 43, like you can't get 43, and some of the ones before 43 you can get. But after 43, and you can either ask a computer or just spend, it's not that long, but spend a little while to do it, you can get that 44, 45, 46, 47, 48, and 49. Is that 49 still visible? Just? Yeah, I can see it before you, but yeah. 1, 2, 3, 4, 5, 6. Let's check. Let's actually compute these to see, okay? So what is 44? How about 4 6s? Oh, that's good. 4 6s plus a 20. All right, I'll like underline the box sizes there, right? Okay, 45 is great, right? That's 5 9s. I'm not saying that's the only way to do it. I just want to show we can get these. 46, also easy, 2 20s and a 6. 47, one thing already worth noticing here, the fact that I could get 45 had like nothing to do with 44, right? And 46 really didn't have anything to do with 45. This is relevant in the proof in a moment. We're getting into something that's called strong induction. I don't want to dwell and I don't want to teach the method any more beyond this, but this is what's happening in the background here. What's 47? 3 9s and a 20. Oh yeah, 27 plus 20, great. And then 48, that seems like an easy one, right? That's like a bunch of 6s would do it, for instance. Is that, how many times 6? 8 6s, okay, great. 49, 2 20s and a 9, yeah? So 2 20s and a 9. And in principle, I can keep going here, but I claim I'm done, right? I claim now I can get every single amount from here and beyond. And let me tell the rough idea, and then I'll sort of inductionify it real quick. Suppose I wanted to do 50. You could sit down and just write it out, but what information helps me find 50 in this picture here? Yeah, 44 I know how to do somehow. Just add a 6 box to it. How do I get 51? Add a 6 box to 45. Add a 6 box, 6, 6, 6, and so on. What if after I've added, that gets me 55. Now suppose I want to do 56. Yeah, I found 50 along the way, add 6 to 50, which is adding 6 to this one, and then that gets me it there, right? So like these give me the next 6. Well, maybe I can even say it, 40, it becomes 50, 51, 52, 53, 54, 55, and then 56, 57, 58. These keep getting rows and rows and rows and rows of 6s. And I don't claim that this gives me like the most efficient way of doing it, right? If I keep doing this process, if I want to get 100 nuggets, it'll be like some stuff and then like tons of boxes of 6s. Whereas like the most efficient way to get 100 would just be 5 20s, right? So I'm not saying anything about the number of ways to do it. I'm just saying it can be done. From 44 and beyond, everything can be done, okay? Now, here's the wrinkle in induction. Ordinarily in induction, we've done some sort of base case, and then we've gone from Sn minus 1 to Sn, or maybe we've gone from Sn to Sn plus 1. That was mostly like a stylistic choice, right? There's no content difference in between doing those two. Here, though, it's not to say it can't be done, but it's a bit of a headache, right? To get 50 nuggets, if I told you, hey, I know how to get 49, it doesn't really help you go up by 1, right? With the boxes you have, there's not really an easy way to go up by 1 nugget, right? There is a reasonable way to go up by 2 sometimes. Can anyone see some way that sometimes you can go up by 2? Yeah, exactly. Or subtract 2 9s and add a 20. Say, if you happen to have 2 9s, you could drop them and add a 20, go up by 2. But so that still doesn't help us. A, you might not have 2 9s. B, I want to go up by 1, not by 2. I don't want to show every third number, every second number works. I want to get them all, right? And so there are still ways around it. There's lots of case analysis where like, well, if you have 3, these numbers aren't even that great actually. Like it's complicated to go up by 1. You have to do a bunch of trading in and out. Actually, what's the easiest way we can go up by 1? Supposing I have like tons of boxes of all different types. Anybody see an easy way to go up by 1? I see it. 20 plus 6. Replace it with 3 9s, right? There's one way. If I have a 20 and 2 and 1 6, I can replace it with 3 9s. But what if you don't have that? Then there's maybe some other way to do it. So what I'm trying to get at is this can work. It's a huge headache here. So what I want to do instead is I want to argue from Pn minus 6 to Pn. And let me pause there for a second. Suppose that works. Suppose that induction allows me to do that. We haven't seen whether that's true or not. If I know the answer for n minus 6 nuggets, we've just discussed a strategy how to get n nuggets. Add a box of 6. As simple as that. That's like the whole proof if we're allowed to suppose this. If we're allowed to suppose that, okay? Now, it turns out whatever strong induction says is you don't have to just assume the prior case. You're allowed to assume all the previous cases. So I am allowed to use the n minus 6 case here, but there's a little caveat here. Normally when we went down by 1, suppose I was doing one of those summation ones or something like that, and I wanted to prove it for 10. Well, I get the answer from 9, and from 9, I get 9 from 8. From 7, I get 8, and so on and so forth. I drop down by 1, and eventually I drop down to 1, and I started with like 1 works. If I drop down by 6s, so I want to get the answer for n, drop down by 6, drop down by 6, drop down by 6, what's a danger there potentially in our sort of old model? Exactly, you need this like safe run of base cases, because like if you draw it this way, say I want to know this n and I know how to jump by 6, what if I jump into the false zone, right? What if I jump down to like 43, which you can't do? Then I can't use the answer for 43 to establish the answer for 49, because 43 doesn't exist. But all I have to do is make this nice buffer of base cases, exactly, Trez, right? I get these 6 base cases. I have 1, 2, 3, 4, 5, 6 in a row that are all true. If I go up here and jump down by 6, I can't avoid landing in there eventually, right? So I make this run of safe base cases, and I get here, this is true, and then I build this answer up by just doing those jumps, okay? That's about as formally as I'm going to explain what happens with strong induction. And you'll see some instances in a moment where we do big jumps and we actually don't need a big run. It's problem specific. It really depends on the problem and how you're doing things. But the point is, you don't have to go incrementally. You can just use any prior case as long as you establish the appropriate base cases. Okay? And so in this case, the proof would go as follows. The base case is do those 6. Just write them down, prove them, do them by hand, use a computer, whatever. Then it would say, if I want to prove it for n nuggets, assume n is at least 50, right? I don't need, this range is taken care of. So n is above 50. And say n minus 6 is at least 44. And I know everything between 44 and n, or n minus 1. So I know n minus 6, use that by induction, add 6 nuggets to it. Okay, that's like the framework there. Okay? By the way, what was the significance of 6? Why didn't I jump by 9 or by 20? See, Natalie? That's the least work, right? Like I could have made a run of 20 and then jump back by 20s, and that's actually like a little more efficient in terms of producing the answer with few boxes, but I still have to do 20 by hand. So, Traz, do you have a question?
Yeah, wouldn't that be the most efficient if you could come up with a run of 20?
I think so. I think that would, yeah.
200 or something, and then you could always use that. Hey, it's the most efficient way to get whatever.
I think it would be, right? Like the most efficient is to use as many 20 boxes as you can. And so, yeah, I think it would. And actually, the row of 20 would start here because we know it always works here, right? And so I could start at 44 and just go up to 63, right? Yeah. And those aren't even that hard to do. And in fact, in problems like these, if you wanted efficiency, go by 20s and solve the first one. Ask your computer to figure out the first ones too. Because some of these weren't the most efficient. I don't know, maybe the ones we made were. Like this 48, could we have done better than 8 6s? Maybe we could swap in a couple of 9s, hey Anna. Maybe, I don't know, right? But like you'd also have to be careful to do the first run efficiently as possible if you wanted them. But yeah, absolutely. So, right. Okay, so let's do some more strong induction examples. This one. Okay, yeah, this one's so cool. I really am fond of this one. Here's what I'm going to do on this one, because I want to speed things up and start getting to some nice proofs. I'm going to tell you when induction's being applied. I'm not going to write out like assume it holds for blah, blah, blah. We're just going to see prior cases here. Okay, so I want to prove, I know that x plus 1 over x is, what did it say, an integer? I'm given that, and I want to show that x to the n plus 1 over x to the n is also an integer. All right, that's my goal here, okay? All right. So a couple of base cases are not too challenging here. So I want to show that this works for all natural n. Yeah, yeah.
This all n as in any integer?
Yes. Yeah, absolutely. Yeah, yeah. Good rule of thumb. Anytime I ever say n today, it's an integer. Actually, that will probably hold for most of the other things. N's an integer, or even mostly a natural number almost every single time. In induction proofs, it's going to, 1, 2, 3, 4, 5, and so on. Yeah, in here also, natural numbers don't include 0, although we've seen some base cases start from there. And then x will typically be some real number, right? Like, to make this an integer, in general, like, x is going to have to be something kind of weird, right, to get x plus 1 over x to be an integer. But what's cool about this proof is I'm never going to tell you what x is. I just know x plus 1 over x is an integer, and that if I take the square, or the nth power of both of those things, I still get an integer no matter what. Which isn't like the most plausible thing here necessarily, but it boils down to how amazing it is to FOIL these things out, right? FOILing out x plus 1 over x's are great, right? Because the middle terms cancel with each other, and that's what we're going to use here. So I want to show this. Let's do the following. So x plus 1 over x, that's an integer, right, by assumption. If I raise it to the nth power, what is that? Still an integer. It's just an integer raised to the nth power, still an integer. Let's FOIL this out. We get x to the n plus 1 over x to the n. Then what happens? Is this the proof I wanted to do? Yeah, it is. Then we get plus 2 times, what? Do we just get 2? Oh, no, sorry. I don't want to FOIL this out. Yeah, we can do that. Sorry. It's embarrassing. I need to use the binomial theorem to multiply this out. I don't want to do that. Yeah, I don't want to do that. Sorry. Let me see if I can remember what I want to do. How about we do this instead? Let's do the following. This is an integer. This is an integer. That one's an integer by assumption. Why is that one an integer? I'm not lying to you, but I'm not saying the whole story. Why is that an integer? Yeah, inductive hypothesis, right? With n minus 1 and n minus 1, that's an integer. So I multiplied 2 integers, I get an integer. Let's see what happens with this one here. I get x to the n. Great, I'm hoping to see an x to the n. I get plus 1 over x to the n minus 2, right? X times 1 over x to the n minus 1 is x to the n minus 2, plus x to the n minus 2, plus 1 over x to the n. Okay? Now we're getting somewhere. I want to show that plus that is an integer. This is an integer. What about this? That's also an integer. Why is that also an integer? It's the case before, and we're doing strong induction where I assume all the prior cases work, right? So this is an integer by induction. This whole product, this individual one's an integer. So is this one an integer? And I don't necessarily need to do the work, but if I solve for x to the n plus 1 over x to the n, I have integer times an integer minus an integer. I get an integer. That's the end of the proof, right? Then these two are an integer. However, what's missing? Here we do need to be a little careful. Everything's fine as written here. Well, yeah, we need some base cases, right? So what did we subtract from n here? We went down by 1, and then we went down by 2. I don't want to be asking, oh yeah, you know what, that's funny. Does that work? So I was going to say we don't want n minus 2 to be negative. But you see what actually happens here? This is wild. Check this out. Suppose I only do one base case, right? Suppose I only did the one base case, which is n equals 1, which is like literally that expression there, and I don't bother to do 2, right? I should do 2, and it's not hard to check. Actually, I don't even know. Maybe I don't want to do that. But imagine n is only 1, and I subtract 1 here. Then I get 1 over x to the negative 1 plus x to the negative 1. Yeah, I actually get this back, which is an integer there. But I have to be really careful because like technically the statement isn't set up in terms of negative ones here. Although, man, I think you can get away with one base case here. So, I mean, yeah, go ahead.
2 instead of 1.
Okay, excellent. Yeah, okay, that's a great question. If n is 2, then I get, okay, I do get an integer, but not by the base case there, because I'd get 1 over x to the 0 plus x to the 0. Maybe I would, yeah, x isn't 0, by the way, right? That's implicit in the original statement, because you can't divide by 0 here. So you would get 1 plus 1, and you'd still be okay, but not because of this assumption, just because of the particularities there. That's interesting. Now, in principle, it would be okay to just check, is that an integer, right? You can sit down and check that one, and that actually works as well. You can, I forget what you do. Maybe you take this and multiply it by itself, and then you get that plus 2 or something like that, and that's an integer. But yeah, it just occurred to me now that actually going down by 2 isn't necessarily a problem. That's really funny. I want to move on to the next one. I'm going to come back to this in my own time and think about it a little bit more. It's kind of, if we can get away with a single base case there, that's pretty neat. Huh. But the key thing that I wanted you to see, right? Multiply this integer by this integer, FOIL it out, and it's like, oh, that didn't quite disappear, but it's still of the same form that we can apply induction to as well. Okay. Yes, QED. Well, I proved it was, yeah, it was a problem. Oh, this is amazing. I love this one. This is my favorite. Okay. And I think we'll see this function again in Hannah's, right? You don't prove this theorem, do you? Okay. Hannah, you remember the name of the function on the left there? Yeah, it's the product of all the primes up to n. I think, not that, I think it's the primordial, or number, that number, the result of that is the primordial number. Not primordial. I thought you made a typo. Yeah, exactly. Yeah. So this is part of Erdős's proof of Bertrand's postulate, which says that between n and 2n, there's always a prime. This is one of the steps in it, and this is an amazing. The induction isn't so hard. There's one number theoretical trick that's just fabulous. And so if you like this, Hannah's going to give you 3 hours of number theory when I finish anyway. Some of which I'll be like leeching from a little bit here without saying too much. But here's what I want to do, and I should explain the notation as well. So here, I'm going to take the product, that's what this notation means, over every prime, so p prime, and p is at most n, okay? So if n is 100, I'm just taking the product of the primes up to 100. So 2 times 3 times 5 times 7 all the way up to 100, right? I mean, 100's not prime, you take the biggest prime up to there. Times p. And this product, I claim, is always less than 4 to the nth power. Is that what's written there? 4 to the n? Yeah, good. Okay. You may wonder why you care about this, or is it obvious or anything like that. It's very, very nice, actually. And it's like I said, it's useful in Bertrand's postulate, but it's a really good induction example anyway. I think it's really great. So, okay. Let me see if I can remember how to do this. So we're going to do induction on n. I promised I wouldn't say this anymore, but we have to be careful. And let's do a couple base cases here to make sure we understand what's going on here. So when n equals 2, there is some question about where should the base cases start here. And n equals 1, things still work just fine. This product here, it would be the product of all the primes that are at most 1. And you may be wondering, like, is that 0? How do you do that? That's the empty product. It's the product of no numbers. It's usually defined to be 1. There's good reasons for that. If you're a computer scientist, I've said this in my other classes before, empty products, and like if you take in Python the product over an empty list, like it'll spit back 1, typically. I hope it should. But let's not bother with that. Let's just start at n equals 2, because then at least the thing makes sense here. So how many primes are there that are at most 2? One of them, and it's 2, and if you multiply all those together, you get 2, and 2 is less than 4 to the 2 by far, right? It's not even close, okay? What about n equals 3? Here you get 2 times 3, right? The number of the primes up to 3 are just 2 and 3 themselves, and this is still way less than 4 to the 3, right? Actually, it seems to be diverging quite a bit there. I think it does. I think 4 to the n absolutely dominates this one. I don't think it's close to it, but it's enough in practice. Okay? All right. So now, what I'm going to do here is I want to prove it holds. I'm going to assume this here and go to the n plus 1 case. Okay? Nah. No. I'm gonna prove it for n. I'm gonna assume it holds for all values less than n. Actually, it has to be a strong induction proof here. Okay. So case 1, n is, say, even. Okay. First of all, I'll add up here that n is at least 4 now. Right? We've handled the n equals 2 and n equals 3 cases, so we're only interested in proving that this works for n at least 4. We should notice something immediately. So when n equals 3, I multiplied 2 and 3 and found that it worked here. When n moves up to 4, what changes? Like nothing changes. I still get the same 2 primes. And actually, I just get more room because now this goes up to 4 to the 4, right? So when n is even, it's actually not that interesting, right? Because then I'm asking the product of the primes up to n. Well, that's identical to the product of the primes up to n minus 1. Everybody agree? That go down by 1, it didn't matter. In the beginning, it's a little tricky because there is an even prime, but from 4 and beyond, the number of primes below n, or the actual primes below n, and those below n minus 1 are identical. And then to this, I'll apply induction, right? That's a smaller value of n. So induction says, oh, that's less than 4 to the n minus 1, right? That's induction. And what's 4 to the n minus 1 smaller than? 4 to the n, right? So this is indeed smaller than what it's supposed to be. That's not interesting, right? Those aren't, that's not the interesting part of the proof. It is interesting when n is odd, because when n is odd, n might itself be a prime, and dropping by 1 loses me a prime, and this inequality no longer holds. So I have to do something different, okay? So I'm gonna erase this, because that's just to get the n even case out of the way, although it is technically induction, okay? So n is odd now. And actually, you can even do more. N is odd. You can actually even assume n itself is a prime, because if n is not a prime and I subtract 1, then I won't lose anything there. But we'll just say n is odd. Okay, so n equals, say, 2 times t plus 1. That'll be the format there. And now I'm interested in the product of the primes. I'll replace n with 2t plus 1, right? Ultimately, I would like to show that this expression is less than 4 to the n or 4 to the 2t plus 1, right? That would prove the theorem. So let's rewrite this product as, let's take the products of the primes that are at most, it's easy to make a mistake here. Let's go up to t plus 1, right? And then multiply this by the product of the primes from bigger than t plus 1 up to 2t plus 1. That okay? Everybody see all the primes captured here are captured. Either they're smaller than this and they're collected up, or they're bigger than this and they're collected up, and then everything's multiplied out. I just split the primes in that range into 2 groups, the small ones and the big ones, okay? What can you tell me about this? Even. It may not be, oh, okay, oh, yeah, Hannah, I see what you're saying. Yeah. Yeah, 2 is definitely in this range. Yeah, you're absolutely right. So the actual product itself would be even. That's true. Yeah, that's a good point. I thought you were referring to t. T is like all bets. T might be even, right? All bets are off. So that's true. It's even. But what does induction say actually here? Yeah, that this is less than 4 to the t plus 1, right? Because t plus 1 is less than 2t plus 1. It's a smaller value. Notice we're using strong induction here, and how I jump back really far. I jump back t steps. I jump back almost half of n. But that's fine. That's what strong induction allows us to do. We fall in the range there, okay. So that one works. That one's replaced. Now, this one, what do we see? What do I need to do for this one? What would complete the theorem? If that's at most what? 4 to the t, right? If this expression here is at most 4 to the t, then I have 4 to the t plus 1 times 4 to the t. In total, they're 4 to the 2t plus 1, which is n, which would establish the statement that I want. So that's my goal. So let's focus on that. Let's look at the product of the primes between 2t plus 1 and greater than t plus 1. Okay, 2t plus 1. I'm going to make a claim here, and then I'm going to establish it. I claim that this is at most 2t plus 1 choose t. Okay? Which helps me get there, which I'll tell you in a moment, but I claim that it's less than this binomial coefficient. And this is the wonderful part of the argument. So, okay, this is a claim. I'm trying to prove this. Let me expand this and just think about what's going on with this expression here. So what is this expression here? This is 2t plus 1 factorial over t factorial times t plus 1 factorial, right? The other term is 2t plus 1 minus t. I get left with t plus 1 factorial. So let's rewrite this as the following. This is 2t plus 1 times 2t times 2t minus 1 times 2t minus 2, all the way down to, actually I was hoping, yeah, I'm gonna say t plus 1, and then I'm gonna put the t plus 1 factorial on the bottom. That also, I canceled with the t factorial. I could have canceled, that's more conventional to cancel with the t plus 1 factorial, but either works. There's a chance I may have flubbed the cutoffs here. We'll see if we can repair it. I think it'll be okay. Okay, so now here's what I want to consider. These primes here. Oh, yeah, you know what? We're fine. Let's go back. Yeah, let's go back. Carter, you said t plus 2, I think, and then this would become t, yeah? That also works. That's a little more conventional. I'm going to do this after all. Now, think about the prime numbers here. They're greater than t plus 1, and at most t plus 2. Each of these prime numbers appears in this numerator. Everybody agree? All the primes are in that numerator. This numerator contains other things beyond those primes, but those primes are in the numerator because the primes live between these two quantities, and all those numbers are in the numerator. Now, that would suggest, let me hide this for a second, certainly that product is bigger than the product of those primes because the numerator contains those primes and some other stuff. But the problem is, because I'm dividing by t factorial, well, I'm dividing by something, maybe it's no longer bigger than the product of the primes. But think about this for a second. In here, some of these numbers are primes, right? Some of them are primes, some of them are not, and then they're divided by this business here. Let me take a step back and ask you, what kind of number is a binomial coefficient? It's an integer, right? It's a round number. So what it means is if I divide by t factorial, am I going to be getting like left over with some decimal, some fraction? No. That means the t plus 1 term, 1 times 2 times 3 times 4 times t plus 1, those somehow divide into the numerator, right? All those numbers get absorbed into the numerator. But in this list, in the numerator, there's some prime numbers. Can you divide something into a prime number? No, they're primes. They don't have divisors. So after the result of canceling these out with stuff up here, I don't know what they cancel with, but I know they cancel because that's an integer. Some stuff's left, but what's left for sure among this after doing the cancellation? The primes, and some other stuff still, but the primes are definitely there. So that means that this product of primes is at most that binomial coefficient. It has nothing to do with the choose function. It just has, we only leverage the fact that this thing was an integer by definition, and that its expression was this, and then we use something that, I don't know if Hannah will actually prove this, but I mean that's the definition of a prime, that numbers don't go into it, right? So okay, fine. We've established this. I needed to get here, so we have to do a little bit more work to get there, okay? Yeah, I see in the chat. This trick is just amazing. It's so cool, right? Isn't it fantastic? But it's only good if it gets us somewhere, right? Like we want to get to the end. Okay, so let's just explore back to this one here. Okay, and so now I'm actually also going to steal from Nana's section, which you have to wait quite a while to get to. But I want to look at this expression here, and I'd like to establish that it's at most 4 to the t. Okay? Now, if you're familiar with binomial coefficients and you've worked with them before, the central binomial coefficients are bounded above by 4 to the bottom there. Like it just does what it does, but let me try and justify it a little bit better than that. Okay. This expression here can be rewritten as 2 to the t plus 1 choose t times 1/2 plus 2 to the t plus 1, choose t plus 1. Yeah, sorry. Yeah, don't worry. Everyone will have forgotten by now. It'll be a totally new audience. And yeah. So let's just check. These two binomial coefficients are identical. This is 2t plus 1, choose t. This is 2t plus 1, choose t plus 1. T and t plus 1 add up to these. There's identities here, but this says picking t things is the same as setting aside t plus 1 things. Nana will literally prove this to you in a more general form. So that's the same as picking t plus 1 things. Okay, fine. So this expression can be rewritten as this expression. But if you were to look at all of the binomial coefficients added together, 2t plus 1, choose 0, choose 1, choose 2, choose 3, choose 4, choose 5, choose 6. That's all of the different ways, stealing more of Nana's stuff. I'm not really, well, I guess I am giving the proofs, but you know, I'm rushing through them. This is a highlight for later. This sum here equals 2 raised to the 2t plus 1. Maybe I won't prove it beyond that. This is a well-known fact. I equals 0 up to n gives you this thing here, okay? So let's go back here. These are two terms in this enormous sum, right? So these two terms alone are certainly less than this. Probably they're not even close because like this has a million other things in it. But it means that this is less than or equal to 1/2 times 2 to the 2t plus 1. Right? And what is this? This is 1/2 times 2 to the 2t plus 1. That's 2 to the 2t. But 2 to the 2t is 4 to the t. And that's this here. And now I have this product here is at most, or less than, 4 to the t times 4 to the t plus 1 times 4 to the t. So it's at most 4 to the 2t plus 1. And that's what we wanted, was this here. That's an all-time favorite. I think it's so cool. And you can continue to use it to prove Bertrand's postulate as well. There's even more induction in that one, but I don't want to go through all those. 216, okay. Chocolate bar, skip. Skip. Yeah, skip.
Okay.
Oh, there's so many good. What do? We do easy ones, or there's like 3 amazing ones at the end that there's no way I can cover all 3 of them. All right, skip. I'm answering my own question here. That's a good one. Let's skip it though, because okay, there's one about pi that I absolutely have to do, and that could even like come close. Yeah, keep going. It's close. No, that's a graph theory one. There's more fundamental theorem. No, keep going. Holy moly. Nope. Yes. Okay. Look, that's crazy, right? We gotta prove it's pi day. Finally, pi count 1. This is pathetic. So. Yeah. Okay. I want to prove this amazing formula. This was the first infinite approximation for pi that was known in Europe. It's like 500 years old, which is crazy too, right? So 2 divided by pi is this wild. Try to read what's going on here, right? You have root 2 over 2, that's fine. Then you have times root of 2 plus root 2 over 2. And then you have times root of 2 plus root 2, root of, okay, I think you can see where this is. Okay, why don't you tell me what the next term will be? It's gonna be divided by 2. It'll have a square root. And then it'll be 2 plus root 2 plus root 2 plus, is that it? I think we got it, right? That's the next term in the C. And you see you can keep making these ones over and over and over again. Okay? Yeah, you can probably give the full screen, perfect. Good, so that's like, yeah, just as a sanity check, do we understand how this product is going? And this is, it's not written as such, but there's the dot, 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 right? This is an infinite product, right? And so what we're really claiming here is that this infinite product converges to 2 divided by pi, okay? And so I want to prove this by induction. And yeah, we'll use a few other things too. Okay, so what do we have to do here? Okay, so this is going to follow from another result that we're going to prove by induction and then plug into it at the end. So I'm going to claim the following. We'll call this a lemma, and this is what we'll prove by induction. So sine of x equals 2 to the n sine x over 2 to the n times the product, I ranges from, I hope, 1 up to n of cosine of x over 2 to the n. Maybe. I think I have it written down here. Yeah. Yeah, I claim this is true. We're going to prove this by induction. All right? Let's check.
That doesn't give us another pi count. I mean, they kind of.
Well, we already used a bunch of those. That's true. I think the LaTeX command for them is prod, but maybe, yeah. Okay, so we got this crazy expression here. All right. I was wondering actually. I think I want it for n equals 1. Let's look at it for n equals 1. Right? We need a base case. Yeah, this is cool. All right, so the base case is asking the following. Does it hold that sine x equals 2 times sine of x over 2? What's this product? When n equals 1, it's just a single cosine. This is a question mark for the moment. Anybody recognize that? That's the half angle identity. So it's true, like, because we learned that in whatever grade you take trig for the first time. I do not remember the proof of this, but probably it can be done with some triangles. But this is the half angle identity, right? Okay, another excellent example of a difficult base case, right? I mean, like, there's a separate proof of this, but because it has an actual name, I think we'll consider it as proved. Okay, that's our base case. I want to prove this thing holds for all n now. It works for n equals 1. Let's try and prove it for, why don't we let's use the assumption that this holds for n minus 1, right? Maybe, I'm not going to write it down, but if we have an n minus 1, an n minus 1, and n minus 1, and n minus 1 here, then that statement should hold. Notice it's kind of interesting. For every value of n, like, it's still sine x, right? The left-hand side isn't changing. Most of the identities we've learned so far in class have been like, oh, the sum of the odds equals n squared, and both signs change here. This is just producing infinitely many estimates. They're not even estimates. Exact values for sine x here. Okay. So I'll say suppose. I'm going to write it down anyway. Partly because I forgot what to do next. So this will give me a moment. 2 to the n minus 1 sine x over 2 to the n minus 1. Times the product, I equals 1 up to n minus 1 cosine x over 2 to the n minus 1. We're going to suppose that, try to establish this up here. How about we use this on it? That's my suggestion here, yeah? So this is true. Let's make a substitution here for this sign. For this sign here, yeah, that's got to be it, I hope. To this sign, let's make this substitution, use the half angle, and see if we get what we want. I think we will, right? So we'll have 2 to the n minus 1, that's this. And then I'm just going to put this in a parentheses before I simplify things. Sine of x over n half is, we get a 2 no matter what, this 2 doesn't depend on n. And then we have sine of x over 2. That's x over 2 gives me sine x over 2 to the n. Everybody agree, right? I just divided this one by, it's this expression divided by 2. And then I also get a cosine of, same thing, cosine of x over 2 to the n, yeah? Same thing, a cosine of x half, and x is that angle there. And then I still have my big product that was inherited before. Okay, and if you just simplify terms, you get what you want here, but I'll write it out, right? So 2 to the n minus 1 with another 2 gives me 2 to the n, great. That's what I wanted there. The sine is exactly what I want, sine of x over 2 to the n. And then look at this product here. This is cosine of, by the way, there's a mistake here. This is an I here, right? Yeah, and here. Right, that should be an I, of course. Otherwise, why would I use product notation if it was the same cosine here every time? So what this product is saying it's cosine of x over 2 times cosine of x over 4 times cosine of x over 8 times cosine of x over 16 all the way up to the nth power. Those you have a bunch of cosines collected. And so that works here too, right? This is cosine of x over 2 to the n, and this is cosine of, wait, something's wrong. Yeah, okay, great. That's just I. Yeah, absolutely. Then -1 is there, right? And so what is this? This product is missing its nth term, which would literally be that. And so this becomes times the product I equals 1 up to n of cosine x over 2 to the I. Okay, so this is true. Okay, by induction. That's the inductive part. Actually, there's a second induction part, but I may not go through the details. Okay, this doesn't really feel like we're that much closer to proving the identity we want, but we do have this nice expression here. Okay, so now a little bit of hand-wavy analysis. This expression, and I hinted at it already, was actually infinitely many expressions, right? What's that? Already? Oh, that is a QED, I guess, huh? Yeah. I proved a lemma, that counts, right? Even if we're not the full proof yet. Okay, look at this expression. This holds for every n, right? Like I get infinitely many for all sorts of n's. What if I take the limit as n goes to infinity of both sides? What happens to the left side? No, there's no n, nothing happens, right? So sine of x is the limit as n goes to infinity of this monster here. One part of it is easy to handle. What is the limit as n goes to infinity of that product? I'm not saying there's an easy substitution, but there is an easy way to write that. Yeah, it's just an infinite, you just put an infinite symbol on top. Like nothing, I didn't actually do anything here, right? This is just I equals 1 up to infinity of cosine x over 2 to the I. I'm not saying this is easy to handle, but like that's just what it is. This one, though, is a bit strange, but it's worth looking at for a second here. So we got sine, right? Where's the axes go for sine? It's like right here. Does that look right? You got to check. I don't know anything about trig, right? I think that's where it should be, right? Okay. So think about what's happening here. As n gets larger and larger and larger and larger here, I'm plugging in an angle, but then I'm dividing it massively by 2 to the n. So if I'm actually trying to compute, sine of this x here, where does like sine of 2x get pushed to? Like in towards the middle, right? The negative and positive x, they get pushed like closer here. This is, I'm not giving a formal argument, just trying to give an intuition. They get pushed into that smaller region there. What is the impact of this thing being kind of out front there? It kind of stretches, it pushes it up, right? Because this is like after computing the x value, this pushes the thing up there. I'll let you guys think about this a little bit, but what it actually ends up doing is this procedure as n gets larger, it just zooms in closer and closer and closer around 0 for sine x, okay? You're just squeezing the x values in this range here and then like stretching it back out in the x there, in the y, okay? That's a very hand-wavy thing, but do you guys know what's the behavior of sine x as you zoom in right at 0? Like if you zoom in with your calculator infinite, whatever, what does it end up looking like? It's just a line. It's like the best line. And actually, this is the truth. This thing converges to x. Okay? That's good, right? We took the limit, we simplified. This thing became an x instead. I am doing some analysis under the hood here. It's not like, is it clear that actually distributing the limit like that is fair? There's a lot that's going on, but this does actually work. Okay? Now, I'm going to simplify this expression here just to divide sine x by x. Okay? It equals that infinite product, okay? So now I have this nice expression, right? It just follows from taking the limit of this and rearranging terms. Now, let's evaluate this thing at pi over 2. This expression here. Plug in pi over 2 on both sides. What is sine x of pi over 2? Yeah, it's 1. What is in the denominator? Pi over 2, so actually what do we get? Ooh, it's getting exciting, right? We're seeing the left-hand side of that expression over there. Now, what do we want this cosine to be? Well, that thing over there. One thing's fine, this is an infinite product, that's an infinite product, okay? Now, we can prove something by induction, but this is induction in disguise. Let's just go through step by step by step instead. So let's compute a few of these values for specific values of I. So for I equals 1, is this right? I think we're right. I equals 1, I'm asking for cosine of, oh yeah. I'm evaluating at pi over 2 still. So at I equals 1, I'm asking for cosine of pi over 2 divided by 2, that's cosine of pi over 4. You can look it up, but you can probably guess what it is. It's root 2 over 2. Fine, so far so good. But the next one starts to get weird. So the next one is cosine of what cosine am I asking for here? Yeah, pi over 2 over 4, right? So pi over 8, okay? Of course, you can ask your calculator what that is. It will not tell you most likely that it's root of 2 plus root of 2 over 2. Like it, you know, but anybody remember the complement of the half angle formulas? There's the double angle formulas. Michael, can you tell me for this, let's work with this concrete value. Or, so cosine, well, okay, let's put it here. Cosine of, say, x over 2. Well, I don't know if you, I mean, it's not fair. I would never ask someone if they know what that is. I just know that it exists. It's, I have it written down. But if anyone knows it, you can yell it out. Yeah, nice. I believe it is 1 plus cosine x all divided by 2. That may look familiar there. You'll have to believe me, this is something that we learned at some point here. Okay, so you can prove a more general formula by induction that involves those, but let's just crank a few more by hand here. So this one here would be equal to root of 1 plus cosine pi over 4 all over 2. Everybody agree using this expression? I get that there. And this is root of 1 plus cosine pi over 4 we already computed is root 2 over 2, and then the whole thing is over 2. And that doesn't quite look like what's there, but it quickly gets you exactly what you want, right? So this expression is, what's the trick here? Multiply by a fancy 1 again. Multiply by root 2 over, is that what I want? What's the substitution here? If I multiply this, maybe common denominator? I'm like losing steam here, you know, like I know that this will be 2, that's what I want it to be, right? Let's see, actually I think there's, yeah, over 2, thanks, yeah, over 2. Okay, that actually helps, so we can ignore this over 2 because that's the one we're asking, and then is root 1 plus root 2 over 2 the same as 2 plus root 2? And yes, multiply by root 2 over 2, is this what I want to do? What's that? The whole expression inside by 2? But wait. Okay, how about, let's see. But I have a root 2 inside the fraction that I don't like. Did I get the angle formula wrong? So I think it's, I've written my notes in such a way that I cannot tell. Can someone just look it up? Yeah, you have a computer open. Look at Wikipedia. Nobody in the chat?
So it's like cosine of 2 theta, is that what we're looking for?
I forget. How do you tell which one's which? I mean, they're both doubling and halving. Like, there's one with a square root, right? Yeah, like you should see what I've written in my notes. This square root thing goes like, it's like here. Like, what does that mean to you, right? Like,
Theta is 2 times the cosine squared of theta minus 1.
well, come on, don't make me do it either. Just tell me, Michael.
But the half angle, is that what we're checking, the half angle? So that's cosine theta over 2 equal to plus or minus.
Yeah, plus or minus. Yeah, I didn't say this, but there is a plus or minus here, but we're operating in the range where we get the
Yeah,
plus.
that one's right.
With the full square root? Okay, good. Then that's the whole issue here. Then we have this square root here, and this square root here. And then it's 1 plus 2 over root 2. And okay, I'm just going to let you do from there, the algebra should work. But, you know, I hope everyone in this room, assuming I didn't make a mistake, can check there. And okay, that doesn't end the proof technically, right? What's next? You'd have to do it for the next, and you'd be applying cosine of pi over 16, but this would be your extra expression. Similar to this, you do a little algebra, it works. If you want, you can argue by induction that cosine of x over 2 to the I equals the root 2 plus the root 2 plus the root 2 plus root 2 all over 2, where this is nested whatever the appropriate number of times should be. I think it's I times nesting, right? And you prove that by using the angle formula and the existence of the prior one and plug in. It's like, I don't want to go through one more induction, although it is pretty charming that this proof has like 2 inductions in one in it. Okay? But there's of course some nice analysis too to get rid of that. Okay. All right, so we can do
3 pies now.
3 pies. All right. Oh, we like, yeah, right. There's like a bunch of pies. What counts? That one?
Anytime we have it on the board.
All right.
So towards the end of the night, we're just gonna be writing pi everywhere.
1, 2. I think that brings us to 5, right? Because the red one was the formula. Okay. I think there's 2 more induction slides. Oh boy. How could I not do Mantel's theorem? But Pick's theorem is next. I kind of want to do Pick's theorem. All right, you guys can help me. So Mantel's theorem is a corollary, or probably my favorite theorem, period. Although this proof isn't my favorite proof. So Pick's theorem, the induction isn't the cool part. The double counting is the cool part. But I think let's do Pick's theorem. It's the easiest to absorb, and it's just awesome. And you all can help me with this. This last one was tough, right? Pick's theorem is so cool. And the proof is amazing. So there's many proofs of it. I think the Wikipedia article discussing Pick's theorem classifies it as a top 100 theorem. By the way, maybe Turan's theorem, the generalization of Mantel's, should be. I mean, the previous theorem literally is my favorite, but yeah, anyway, this one's easier to understand. And again, the induction's not the biggest part, really. The setup, the lead up to it is instead. Okay, so let's try to absorb Pick's theorem here, right? So I create a shape in the integer lattice. All right, so I have points at integer coordinates. And I create this shape in such a way. It's a polygon. As you can see in the picture, it doesn't have to be convex. It can be concave. It can be a total mess here. But the only requirement I make is that the corners, the vertices of it, are actual lattice points of the thing there. The lines, you notice, don't always fall along lattice points, although I think there is one line there, right? You can see in the bottom left corner there that just so happens to have a blue dot on it as well. That can happen, right? In fact, you could even have a vertical boundary that hits a bunch of lattice points, but it doesn't have to in general, okay? So the only requirement of it is that its corners are at lattice points. And then the question is, what is the area of this object? Like actual area, not number of lattice points, like the legitimate area as a shape in the plane, right? And you could compute it, right? You could slice it into little cross sections and try and compute distances and maybe use Pythagorean theorem and just go nuts with it and find the area. But Pick's theorem has this absolutely amazing identity here that says, all you have to do is count up the boundary points, which I put in blue, right? Count up the interior points, what I put in red, and then plug it into this simple formula here, okay? So for instance, the picture that I actually have here, what is its area according to the formula? Can someone tell me? So A equals I plus B over 2 minus 1. According to that, how many points are on the interior of that? I can't see them too well. Do people agree with 11? Okay, so this should be equal to 11 plus, how many are on the boundary? Is it 6? Let me check. 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5, 6. Yeah, 7. Notice, it is a 6 gone, but there happens to be one more boundary point on the boundary that's not a corner here, right? Those count. So then we agree it's 7 over 2 minus 1. And you can tell me what this is, but that's the area of the shape. Okay? Doesn't matter if you tried to compute it in some other fashion. You get that area. This formula always works. So I want to prove this works for every shape here, right? I mean, like, we didn't prove anything here. According to Pick's theorem, the area is this here, but like this doesn't convince you necessarily. In some of the warm-up examples, we'll see that it's true for some simple shapes. Whew, I'm getting tired and hungry. Oh, okay. All right, so the first couple examples I'm going to do are both examples, but they also help us. They're needed in the proof. So let's first confirm the theorem works for rectangles. Okay, so let's say I have a rectangle. Rectangles are really nice. When I talk about a rectangle here, I mean a rectangle whose sides are perpendicular and parallel to the axes here. Like, there are other rectangles I could rotate and stuff. The formula works for those as well, but I want to work with the simplest one here. So let's say this rectangle is m by n. Okay, we have to be really careful in what I mean by m by n. Here I mean m dots by n dots. Everybody understand what I mean by the rectangle there? So like this is the rectangle here. And I want to know its area. Okay, and its actual area, like not the number of points, although I need those to determine things. Let's figure out its area using what we know about areas. What's the area of a rectangle ordinarily? Yeah, length times width or height times base, whatever, like the product of the two dimension things, right? Here, let's figure out what those are, because it's not m and n. It looks like it at first, but it's off by 1, right? What's the height here? The lattice points are all unit distance from each other. So this is distance 1, 2, 3, 4, 5, 6. How many dots are on that side? 7, right? So the actual height is m minus 1. Everybody agree with that? That's the distance along that, even though there are m points. So you just have to be careful with my labeling here. Except for this first example, I'm almost always just concerned with number of points, because that's what the formula tells me. But the actual area is not m times n. And what about width? It's going to be n minus 1, same thing, right? So n minus 1. Okay. So that's the area of this, according to, I don't know, elementary school geometry, like whenever you learn this stuff, right? This has nothing to do with Pick's theorem. Now let's compute the formula of this according to Pick's theorem. And if it equals that there, then the theorem is true for rectangles, right? So let's check what it says here. Okay, so Pick says that the area should be interior points plus boundary over 2 minus 1. Let's plug in the appropriate values here in terms of m and n. First, how many interior points are here? Yeah, everybody see that I can't use the boundary, so I shave off each of these sides here. And this box here it lost 2 vertically and 2 horizontally. So the number of interior points here is m minus 2 times n minus 2. We're still using the same basic rectangle thing, but it's just on the lattice points. Is that okay with everybody? That's the number of red points here. Don't I have red? All right. Now, boundary points. Boundary points are, how many boundary points are here? Yeah, literally m, right? How many are here? Also m. So let's put, I should have put that in red. Well, okay, so m, 2m for the two sides. How many boundary points are left on the horizontal? n minus 2. Everybody see the corners already get counted by vertically, so there's only an extra n minus 2 there and an extra n minus 2 there. So 2m plus 2 times n minus 2 all over 2 minus 1. This is a plus here. Everybody agree? I plugged in interior, base divided by 2 minus 1. That's what Pick's formula says to do. Now let's just do a little algebra. We'll see that it equals this. Actually, the easiest thing to do here, this is the area that we know. Let me multiply this out. This is mn minus m minus n plus 1. Just FOIL it out. FOIL this out, you get mn minus 2n minus 2m plus 4 These 2's cancel. Plus m plus n minus 2 minus 1. We okay with everything here? Now let's cancel. N cancels with the 2 in front of that. Wait, yeah, that's minus 2n plus n. So yeah, we have m times n minus n. That 2 cancels with that m, with minus m. And we have 4 minus 2 minus 1 plus 1. So Pick's theorem says the area is that, and the area is that. So what does this mean? Yeah, for rectangles, Pick's theorem correctly calculates the area, okay?
Or is it not that simple?
Very close. That's the next step, actually. That's like literally, now we're going to do triangles, and it gets really cool because there's a little wrinkle, but yeah. So rectangles, it works. And this wasn't just to help you understand what's going on. We literally need this. Like, this is part of the proof. Okay, so now let's do right triangles. And you already start to see why things are tricky here. So right triangle. So say I have a right triangle like this. It may not be 45, 45, 90, but so let's say it has some points along there, some points along there. Here's where we already run into trouble. What can you tell me about this diagonal? Like, some might be on it. What's that?
I can tell you a whole lot of nothing.
Yeah, a whole lot of nothing. Exactly right, right? Like, it depends. I mean, you could do something. If you knew this length and knew this length, you can look at angles and figure out if it hits the points on the lattice or not. But like, just look at the curves here, or the lines here. Like, some that one happens to hit one, because it's like 45 degrees is going to hit a lot. But other angles might miss them entirely. It depends. So I'll put a couple hypotheticals, but those won't be a part of it. But that's the problem immediately is I don't know how to apply Pick's theorem to this without getting in deep into the weeds in geometry and trig and stuff. I don't want to do that. We already did that, right? We're not going to do it again. So instead, what I'm going to do is turn this into a rectangle. Okay? So now I have this diagonal in the rectangle, and I have all this stuff here. And let me give some names to things so we can actually figure this out. So in all the cases that I'm working on, the thing I'm trying to find, it has area A, it has I interior points, and B boundary points, okay? And then I'm going to define the corresponding area, interior, and boundary for other shapes along the way. So for the rectangle here, the rectangle that I've created, it has, let's say, area A sub R for rectangle, boundary points B sub R, and interior points I sub R, okay? What do we know about these values? We know that they satisfy Pick's formula because we proved that rectangles work. So we actually know whatever these values are, they obviously depend on these somehow, but whatever they are, we know by Pick's theorem on rectangles that AR equals IR plus BR over 2 minus 1, right? That's the relationship between those there. Now, there is a relationship. Let's write down further relationships that we can observe here. What can you tell me about the relationship between area of triangle and area of rectangle? Yeah, that's half. That's normal. That doesn't have anything to do with boundary points. Like, that's just the area. So we also know that area A of the triangle is 1/2 area of rectangle. Okay, we have a little more relationship. I'm also going to add in something here. I'm going to break down the boundary points into two types. Okay, so boundary points equals BS plus BH. This is the hypotenuse. These are the other two sides. Okay? Everybody agree? Maybe I'll make this a little bit clearer. That in this triangle here, the size of the boundary is this plus this plus this. And so I can break it down into those two categories. The number of boundary points on the sides, like maybe I know something about it, it's kind of nice. But the boundary of the hypotenuse we want to avoid, right? We discussed that's really complicated, depends on a lot of things. But is there a relationship between the boundary points of the triangle and the boundary points of the rectangle? Yes, yes, and that's, okay, so let me write this. That's absolutely right, Michael. Let me put this. The boundary of the rectangle is 2 times the boundary of the sides of the triangle, right? The interior, these boundary points on the triangle are not part of the boundary of the thing. Yeah,
Twice.
very good. Yes, exactly. -2, right? Because look at this. The boundary, I'll put it in, what's boundary? Blue? The side boundary of the triangle is these points here and these points here. That's BS, right? And then if I add this one and this one for the remainder of the rectangle, that point gets duplicated, so does that point there, right? So there should be a -2 to even things out. But do you agree otherwise that the boundary of the rectangle is basically 2 times the side boundaries of the triangle? It's ignoring the hypotenuse entirely, but it should. The hypotenuse is interior to the rectangle. That's an important hint. It's interior to the rectangle. So what can you tell me about the interior of the rectangle? How can I relate that to the triangle? The interior of a triangle is I, right? So the interior of the rectangle is, this is interior points, is what? 2i, yeah, 2i plus the boundary along the hypotenuse. Everybody see? All the points inside of this rectangle, they're either here, that's interior of triangle, or here, which is identical to the interior triangle, or they're the ones that hypothetically live there. There might not be any there, but whatever they are, they're interior to the rectangle, even though they are a part of the boundary of the triangle. Now, here's the dirty trick, is that when we do some substitution here, the BHs are going to vanish, and so we never had to know what they are, even though they have to be written down in the formula here. Okay, so what is our goal ultimately? Ultimately, our goal is to find A in terms of I and B, right? We want to see that formula for the area of the triangle. So let's see what happens if we just attempt. So area of the triangle is 1/2 area of the rectangle, right? We just use that one there. Area of the rectangle, well, it's a rectangle. It follows Pick's formula, right? And so it is the interior points of the rectangle plus the boundary points of the rectangle divided by 2. Boundary rectangle divided by 2 minus 1. Yeah? Now, I'm hoping to get everything about this area in terms of just I and just B. So I want to get rid of IRs and BRs, so I want to make appropriate substitutions. Well, here's one. Let's plug in 2I plus BH here. I don't know what's going to happen here. I cannot remember the details, but I mean, we've done everything right so far. So 2I plus BH. Okay, whatever. Then plus, what can BR be replaced with? That there. Right? And okay, it's BR divided by 2, so I just get BS minus 1. So plus BS minus 1, and then that minus 1 is still there. How does that look to everybody? I just made substitutions there. Now, the final wrinkle is the following. Something's bug. No, it's amazing. It works, right? Boundary of the hypotenuse plus boundary of the sides is what? That's the boundary. Right? I never knew what B of H was, but that's the boundary by definition. So that circled thing could be replaced with B, and let's multiply through by the 1/2. 1/2 times 2I gives me I. 1/2 times the boundary is the boundary over 2. And then lovely, minus 1 divided by 2 is minus 1. It works, right? That's the formula of Pick's theorem. We never knew what was on the hypotenuse. Isn't that amazing? I think that's totally awesome. But it's like the hypotenuse is like interior to the rectangle, and anyway. But we still only got right triangles. We like made marginal progress. But notice we needed to know the formula worked for rectangles, okay? Now I'm going to prove it for, yeah, good, so it's the same question. I'm going to prove it for arbitrary triangles. This was right triangles. They were really nice. Arbitrary triangles are a total nightmare because all their edges are like weird and diagonal, and who knows what's going on with them. But let me draw a picture and then you'll see roughly what to do. So again, now we know the formula there works for right triangles and for rectangles, so we can use those. All right, this next one is a little much, but we have to go through it because it's so satisfying when it works. I mean, that was pretty satisfying, right? So, okay, arbitrary triangle. And then after that, the induction is actually easy, so, yeah. Okay. Hannah, I'm going to run over a little bit, but okay. But it won't be too much. It won't be too much. Okay, now arbitrary triangle. Let me see if I can draw a good picture here. Yeah, that's a pretty arbitrary looking triangle, okay? Let me embed this in a rectangle. Purple, I want purple. Okay, so the triangle in the middle has area A, interior points I, boundary points B. I want to find that it satisfies the formula there, okay? How are we going to do this? What do you see in this picture? A bunch of triangles, and not just triangles, right triangles. Okay, so I'm going to give names to a bunch of things. This one has A1, B1, I1. I don't know why I keep mixing the order, like you guys know what I'm referring to, right? This is A2, B2, I2. This is A3, B3, I3. And I'm going to need the formula for the rectangle bounding the whole thing as well. So the rectangle, again, will be area of the rectangle, interior of the rectangle, boundary of the rectangle. Those are its stats, right? So now everything has names here. And now we want to do what we did before and get tons of formulas for things in terms of each other and plug in stuff and hope that we get the formula. And it totally works, but there's a couple wrinkles we have to be careful with. And I mean, I haven't written down what the exact formulas are, but let's see what we can gather on our own here, right? Maybe, how about the first thing? Can you give me an area relationship? Excellent. Everybody see that? The area of this triangle is the area of the full rectangle minus the 3 individual ones there. And I think writing it that way is a really good idea because we know ultimately we want to see A equals something. We could if we wanted. I'll just do this for a moment, right? That's a rewriting of what Rohan said, but actually we ultimately are going to want to solve for A, so I think I'll put it in that form. So A equals AR minus A1 minus A2 minus A3. Great. So now this is what's so useful about this is I know the formula for AR. I know the formula for A1, A2, and A3 because Pick's theorem holds for rectangles. It holds for right triangles, of which these all are. So I can plug in those things to them. I'm not going to do that just yet, but I think we will have to do that in a moment. But the problem is, suppose I do that, then I see IR, BR, I1, B1, I2, B2, I3, B3. I don't want those. I want I and B, right? So I also need relationships between boundary points, interior points, everything like that. So how about boundary points? I think we can get a nice boundary relationship here. So yeah, luckily we don't have to name the hypotenuses in this case here, but that in principle is there. But luckily, what can you tell me about a hypotenuse in this picture? It's part of 2 triangles. It's the hypotenuse of a right triangle and one of the side lengths of the other triangle. And so somehow they don't compete with each other, right? Imagine I did the following here. What if I add up roughly, let's just say it roughly, and then we have to be careful with double counts. If I added up the purple boundary and the boundary of the interior black triangle, then what have I done simultaneous to that? I seem to have added the 3 boundaries of these guys here, right? With potential overlap we have to be careful of, but they're the same, right? Every one of these edges contributed to the rectangle in the interior triangle or to one of the bounding triangles there. So let's write it out and then just double check. So if I take the boundary of the rectangle and add to it the boundary, that's of the interior triangle I'm interested in, That seems to be approximately, I'll just put this for a moment and then we'll repair it. It seems to be the boundary of triangle 1 plus the boundary of triangle 2 plus the boundary of triangle 3. But it's not quite that, right? What happened here? Yeah, the corners are getting counted too many times. And I think, which corners? This point, it got counted by the rectangle, and it got counted by the interior triangle. But how many times is it actually, oh, wait, what? Is this okay? Yeah, I think you're right. Maybe this one works, right? Because it also gets counted by this triangle and this triangle twice. And so I think the overcount balances out on both sides. Let me just double check my notes. There is an overcount somewhere, but maybe this is not the one. I mean, I shouldn't have to check, right? We've just reasoned it out, but you know, like I'm hardly on my feet anymore here. Yeah, exactly. They cancel. Boundary, yeah, perfect. So these are actually equal. Everybody see that? That like, this gets counted 2 times, that gets counted 2 times, that gets counted 2 times, but that's true on both sides. So the -3s cancel out from one another. So, okay. So that's area, that's boundary. What's another relationship we probably can make? Interiors, right? So how about the interior of the rectangle seems to be the sum of the other interiors, almost, right? So the interior of the rectangle definitely includes the interior of the actual, this one, right? Plus the interior of 1, plus the interior of 2, plus the interior of 3. But that's not the full interior, right? What else needs to be included? Yeah, plus, oh, B alone, right? B alone contributes. The boundary of the black triangle, but almost. We have the -3, right? Because now this point is on the, those are on the corners of, those are on the boundaries of the black triangle, but they're actually part of the boundary of the rectangle, so they shouldn't be counted in its interior. Whew. So -3. So that's where the -3 is showing up that I was anticipating here, okay? But does everybody agree? Whatever these points are on the boundary, they're interior to the rectangle. Notice again, we did this hack, like, I don't know how many there are on any of these individual ones, but I can still talk about them. Is this enough? This feels like it's enough. Let's see what happens. If it's not enough, we'll make more formulas. Oh boy, okay. Still, it's really sweet when it works. Let's take this formula here and do substitutions to it, okay? So I'm gonna just rewrite it here. Area equals AR minus A1 minus A2 minus A3. And what does this equal? AR is a rectangle. We can use the pick formula on it. So it says it's IR plus BR over 2 minus 1. I'll put that in parentheses. And then for each of these, I'll just put a big minus out front of all of them. But what happens here? I get the interior of A1, interior A2, interior A3. Then I get minus boundary, boundary, boundary all over 2. So minus boundary 1 plus boundary 2 plus boundary 3 all over 2. And then minus 3, right? Each of these actually becomes plus 3. Everybody see, right? Pick's formula has a -3, but all of that was interior to the negative that I pulled out of this. So this is actually a +3. Okay? So all I used was Pick's formula 4 times there on shapes that I know satisfy Pick's formula. Okay, so what do we want here? I don't want to do all the substitutions, but we have a nice one here. IR, which is here, is I plus I1, I2, I3, but then I1, I2, I3 are subtracted here. So this becomes I plus B minus 3, but there's a +3 here. So this and this cancel, and this cancel. Yeah, this is maybe verboten. I'm canceling things in different formulas, but I hope I'm making a substitute. I don't want to write everything out. So this here became just that. Now, how about we make a substitution for BR here? Yeah, oh, that's amazing. So I'll write BR as this minus B. Right, it was BR plus B is the BIs. So I moved it over there. And now substitute this in for this. And what do I get? Positive B1, positive B2, positive 3 all over a half. Negative B1, negative B2, negative B3 all over a half. This cancels with these. And I have oh, yeah. This B is here. This negative B will be over a half here. But that's fine. Right? So this guy here plugged in this, and that negative B was what was left over there. It's over 2. And then there's still this minus 1. But everything else, that's been handled, that's been handled, that's been handled, that canceled, that canceled, that canceled. So I'm left with this. And do you see that's the answer, actually, because this is I plus B over 2. Right? B minus B half minus 1. Yeah? So now any triangle satisfies Pick's theorem, not just right triangles. That's the base case of the induction, okay? Right? That's the base case of the induction. Induction is by the number of sides of the polygon in question here, okay? So, and this last part, there's still one more similar formula. I'll write it out. Yeah. Okay. Yeah, good. So arbitrary triangles now work. And in a sense, here's how the argument works. Suppose I wanted to know an arbitrary quadrilateral, right? What would be your strategy here? Yeah, split it into 2 arbitrary triangles, apply the formula to both of them, do similar substitutions, hope for the best, and it works, right? How would you do a 5-gon? There's actually 2 ways. You could split it into a 4-gon and a 3-gon. You can actually split it into a bunch of 3-gons. There's several strategies, but I want to show you a general one where I turn an n-gon into 2 smaller gons. So it's actually a strong induction. Okay. And this uses a little bit of discrete geometry I'm hiding from you. I'm not going to tell you, but it's okay. It's just like believable, so you don't have to worry about it. Okay, so now arbitrary polygon. Well, let's say arbitrary n-gon. Okay, so when n equals 3, we did it, right? We already did it. That was all the work for the base case. Actually, this is definitely probably one of the best examples of hard base case, pretty easy inductive statement. Okay, so now let's suppose I have an arbitrary n-gon. Something like that, I don't know. So, okay, it has its regular A, I, and B, right? Help us in finding the boundary points. Like, we do not want to do that, but they are something. Okay. So this is an arbitrary n-gon. It has those values there. I know that any smaller gon, n minus 1 gon, n minus 10 gon, n minus 3 gon, it satisfies the formula. How can I turn this into a smaller gon? What would you do? How do you turn a 5 gon? Yeah. How about here? You have a lot of options, actually. The fact that there is a diagonal here between points that's interior that splits it in 2, not totally trivial, right? Like if it's a convex n-gon, just take a diagonal, boom, you're done. But that it's wildly concave, like it's not implausible that I can make all these slices in such a way I can't cross over, right? Yeah, I mean, you definitely can, right? And here I intentionally didn't do a triangle just because it's a little more fun. But yeah, triangles are typically going to be safe there. Yeah, absolutely. Right? But even cutting off a triangle is like, it's not quite to the level of Jordan curve theorem, but it's like yeah, it's obvious, but there's a little to do, right? So, but let's draw it here, okay? So we added this blue line here. Appropriately, that's part of some new boundary, okay? And so now let's do the following here. This guy here has A1, I1, B1. And this substitution's easier than the previous, so we won't be here much longer. A2, I2, B2. And then I need one more thing. This little strip here between 2 corners, it potentially is hitting lattice points, right? And it is the boundary of this shape on the boundary and on the boundary of this shape. I'm going to name these interior, well, not interior, I shouldn't say interior. The boundary points interior to the line, I'm excluding these 2 corners. Although if you included them, it'd be fine to just cancel out somewhere else. I'm going to call that x. That might even be 0, but it's the number of points along that line there. Okay? And now, again, we have to do sort of the same strategy as before. Let's try and write out formulas here. So what's the easiest formula I can relate here? Yeah, area, right? The area of what I want is the area of the first thing plus the area of the second thing. Notice this one's easier. In the previous case, I was getting the area through subtraction from a rectangle and the formula is complicated. Here it's the straightforward thing. Area of the full thing is this plus this. It's more like the two triangles into a rectangle case. So this is good. Okay. The two shapes that I've split it into, they have Pick's formula holds for them. Why does Pick's formula hold for these two shapes? What's the magic words? Induction, right? We're doing, this is a whole section on induction. These shapes have fewer than n sides. They're not n-gons. The induction's on n. They have fewer than n sides. They might have as many as 3, as few as 3, but they definitely have less than n. So they're both gone, you know, less than n-gons. Less than n-gons? I don't know. Yeah, I mean, it makes sense what I'm saying, right? I never heard of this expression, but sub n-gons. That's good. So Pick's formula holds for them. So let's plug in. So A1 is equal to, yeah, okay, this is good. It's equal to interior 1 plus boundary 1 over 2 minus 1, and area 2 is interior 2 plus boundary 2 over 2 minus 1. Now, as before, I want this in terms of i's and b's, so let's find out formulas for those. Right? And x is, you know, hasn't reared its ugly head yet. X is problematic. So how about relating relating area was easy. What's maybe the next easiest to relate? Yeah, I mean, yeah, I can't even tell. Like, so let's try and relate here. The full boundary is approximately what? Yeah, approximately the area of the other two except for, right? So it's definitely boundary 1 plus boundary 1 plus boundary 2, except, yeah, and let's be careful here. I think we have to subtract twice x, right? Because when I take the boundary of this, I reach here, and in this case, check 1, 2, 3 on the boundary. And then when I do this one, I also check 1, 2, 3 on the boundary, right? And that's not part of the boundary of B. So I think I need to subtract 2 times x, right? Because those are not part of the boundary of the larger one there. Yeah. Yeah, okay, so that's true, but I was careful to say x is the ones that are within the strip there, not the corners. Oh, I see what you're saying. Okay, good. Right. Those are counted twice, aren't they? So I should do a minus 2. Very good, very good. Everybody see that? They're not a part of x, and so maybe including them in x might have been better, but it won't matter. But when I go around this one, that corner gets counted, and then go around here, it also gets counted. So those two get counted twice. Excellent, very good. What would have happened is we would have reached the end and we would have like minus 2 or something instead, and then, yeah, great. Okay. So that seems to be the boundary formula, and I'll be able to plug it in up there, no problem. What about the interior formula? What is it roughly? The interior of the other two, right? I1 plus I2 plus x, I believe, right? Because, and that's why I didn't choose the corners, because if I choose the corners, they're definitely not part of the interior, although then it'd just be a minus 2 there instead, like it works out. But I think we have to add x, because the x points here are not interior to this or interior to this, but they are interior to the whole thing there, okay? And so now the final substitution is to put these into this and see what happens. So, okay, it's not formatted in the way that I want, but maybe we can do it anyway. So just go down here. And this is the final stage of the proof here. So I1 plus I2 is I minus x. So I minus x. And now B1 plus B2 is b plus these two, and then I have to divide that by 2, yeah? I think. This is b plus 2x plus 2 divided by 2. Do we agree with that substitution there? Right? That this b1 and this b2, I'm just thinking of them in the numerator as over 2. That's these two. And this, solve for this, you get b plus that plus that. Move them over to the side there. And then I put the divided by 2 back here. And then I also had a couple of minus 1s there. So there's a minus 2. And now you can see we get interior, and then look what happens here. Plus b over 2. We have negative x here and positive x here. The x's vanish. They cancel each other out. And then we have plus 1 minus 2 minus 1. Can you believe it? Isn't that amazing? And that's the end of the proof, right? We used induction to finish the part up there. So Pick's theorem works for everything. Actually, there is a follow-up. Yes, very good. That was a tough one, but that was a QED. I did not catch up, at least. That's like order of magnitude. Yeah, I mean, those were all lemmas, absolutely. Those were, yeah, okay, I'm giving myself, so triangle, rectangle, arbitrary rectangle, triangle. Yeah, I win. Okay.
You just felt the arbitrary rectangle twice, though?
What's that?
Kind of the arbitrary rectangle twice.
Arbitrary, I don't know. Maybe, we'll have to think about it. We'll run it back, right? So one thing I want to part with here real quick is this can be extended, right? What if you have a polygon with a hole? Like a part of it, so what if here's the shape, right? Okay, and this part is not part of the interior, right? Like I have a thing, the formula still works here, right? That's something you can think about how to make that work. I don't know where it breaks down. It also has applications, I would rather say versions in higher dimensions too, right? This question makes perfect sense in high dimension, right? Make a 3-dimensional body whose corners and lattice points in the, z cross 3 or z to the 3rd. And I don't know what the formula is for that, but there are different things like that. And people do active research on extending like Pick's theorem and versions of it. It's amazing. So maybe, yeah. Yes. When extending, we still have to be on the lattice. I don't think anything works if you're not on the lattice, but yeah. I mean, then you're just asking, like, then you need calculus, right? Like, so. Okay, I think the final slide, I don't even want to talk about, but you can put it up, Nana, for people to think about, and you can put it on full screen there. Maybe I'll say a few words. So we tried to get conjectures in every one of the sections here, but there's no conjecture about induction. Induction is a proof method. You don't make conjectures about it. Here's a conjecture that's really hard to prove, and induction does not work for it. So it's, when you look at it, it has the feel of an inductive type argument, right? So, okay, I guess I'm talking about it a little bit. So what does this conjecture say? It says, look, if I give you a number n, perform the following algorithm on it, right? If the number is even, divide the number by 2. That's the first step. If the number's odd, multiply by 3 and add 1. That's all you do, and you just keep doing that as long as you want, right? Let's do an example. All right, sorry, Hannah. I'm just like so let's take, I don't know, what's our favorite number to do here? No, it has to be an integer. Okay, that's really good, but okay, I'm gonna do, I looked at it this morning and there's like, I forget, there's one number that takes a lot of steps, but I don't want to do that. Let's do 12. 12 is always a good number, lots of divisors and stuff. So if I take 12, it says that's even, so what do? Divide by 2. So I get 6, and then I feed it back in. I just did recursion here. 6 divide by 2 again, get 3. So actually, if you want to soup it up, you can just see, I'm just dividing out by as many 2s as I can right away. But now 3 is what? It's odd, so I multiply by 3, add 1. I get to 10. Back to an even, but something very different. Divide by 2, I get 5. Multiply by 3 and add 1, I get 16. What happens to 16? It reaches 1. You just keep slicing it in half, right? 16 technically goes to 8, goes to 4, goes to 2, goes to 1. And the question asks, if you feed in any number to this, does this procedure always reach 1? It's not proved, right? It's amazing. There's tons of like computational evidence for it. I don't know up to what number it's been checked that it works, but we don't know that it holds in general. And I think when I looked at the data, the early numbers, like the first 2 or 3 or 4 digits, they like kind of vary wildly. Like some take a long time, some take a short time. But as you go further out, like everything converges fast actually. So it's like seems very plausible. But there's a few random numbers that like jump up and take a long time. But yeah, it's like totally open question. It appears to be extraordinarily difficult too. But anyhow, okay, thanks everyone. Hannah's going to be up next. I think we'll take a few minutes break though before that. So.